welcome back to day 2 of the Dyndrite Developer Conference. I'm Kristen Mulherin and I'm moderating this 2-day event. As a reminder before we get started, please be sure to use the Q&A at the bottom of your screen to submit your questions for each speaker. We have allowed time at the end of each talk to address your questions. This also includes the keynote, so don't forget. Today we have a lot of great content to share. We're going to kick it off with our keynote speaker, Anthony Graves, HP's Head of Software Product and Strategy for Digital Manufacturing. After this, he's going to have a chat on site with Sean Hilbert, the president at Cobra MOTO. After the break, we'll have a series of short presentations from NVIDIA, ANSYS, XAAR, and the CEO at Aeon 3D. They're all 20 minutes or less, including questions, so we're going to go over quite a lot in a short period of time. Anthony will be returning at the end to join our closing roundtable discussion on the future of digital manufacturing, along with Dyndrite CEO Harshil Goel, the president of Cobra MOTO, Sean Hilbert, the CEO at Essentium, Blake Teipel, Dan Brunermer from X1, Gareth Neal from XAAR. With that said, let's get started.
We still seem to be dealing with some of the same software limitations we had going back to the beginning. We need to be able to think about things on a mass production basis. Additive needs to graduate to the level of efficiency that we see in some of these other more traditional technologies.
The future of additive is production. HP has decades of experience automating the commercial printing industry from business cards to books. Our tools at their core need to be able to support massive amounts of data and process this data very quickly. This is why HP's collaboration with Dyndrite is so important.
Dyndrite's mission is to fundamentally change how geometry is created, transformed, and transmitted on a computer. Just as PostScript and the Motorola 68K enabled the desktop publishing revolution, Dyndrite and GPUs will define digital manufacturing. Imagine the wonderful things that people will create, the lives that will be improved, and where humanity will go as a result of this. That is the promise of additive manufacturing.
The companies that will dominate manufacturing for the next 30 years will be choosing their technology over the next 24 months. Choose wisely.
Please welcome founder and CEO of Dyndrite, Harshil Goel.
Hi, folks. Welcome to DDC Day 2. I'm excited to show you guys what we have in store for you today. There's a bunch of cool talks coming up across all facets of our industry. But first, I'd like to kick things off with a bang by introducing a good friend and the head of software, product, and strategy, digital manufacturing at HP. That's a mouthful, so we're just going to call him the bull of HP, Anthony Graves. Anthony?
What you meant by that nickname, but we'll just say that I'm loud. So I appreciate it. And yesterday was awesome. Congratulations on a great day 1 of the DDC 2021. We were a sponsor, HP was last year, for the inaugural event. We were also the inaugural member of the DDC. And so we're excited to be back. We're excited to share some brief updates on what we've been doing. I'll tell you, all the speakers yesterday were fantastic. Sam was awesome. I love to see what SLM is doing. I know you guys are working very closely with them on some special projects, and we're helping out a little bit there. Blake, is always, great guy, phenomenal business, really interested to see what he's doing in that FDM HSE space. Of course, Eve is always probably the most enthusiastic and positive person I think I've ever met. And I'm glad to see that. And of course, Dan from X1 and all the folks, all the members of the DDC, really fascinating what everyone's been able to do over the last, I guess, 6 months, 6 to 8 months since I think, well, maybe it was a year since DDC it was, because it was, you took the place of Rapid last year. You're doing the same thing this year. So fantastic event. And we're excited to be part of it. So thanks for having us.
Thank you for joining, Anthony. And I'm honestly excited for the tour. So I'm just going to mute myself and let you take it away.
Awesome. Thanks, man. And again, thanks everybody for tuning in. We really appreciate it. I know people are getting a little wore out over webinars. Most of us live our jobs almost hourly, taking part in some Zoom meetings. So we really do appreciate you taking time out of the day to watch this live. I'm actually at a remote location that we'll disclose pretty soon, but we wanted to come out and visit a customer. Before we do that, we have some cool stuff to talk about. I wanted to give you just, if you don't know who we are the Software Data and Automation Group inside of HP. And if you watched any of the previous presentations that I gave a little bit of a background. I think it's important because most people think of HP either as an industrial printing company or a computer company, or maybe even a 3D printing company. But several years ago, Christoph Schell, who's now our Chief Commercial Officer here at HP, was a president of 3D print and digital manufacturing. And I joined the company back in June of 2019. And when I was there a couple of weeks. I went to a press event where Christoph and the team from 3D Print were introducing a new 5200 series printer. And what was interesting, I hadn't met Christoph yet face to face. We had talked over the phone. But when he introduced himself as the president of 3D Print Digital Manufacturing, he made it a point to tell the media that he said, you know, as much as we're focused on the 3D print industry, he said, we look at ourselves as more of a solution provider for digital manufacturing solutions, and 3D print is one part of that. And so my team, along with all of my other teammates under Ryan Palmer, we were tasked with taking and focusing on areas that the other software companies hadn't really been focused on. So you have traditional MES in addition to ERP and other big systems like that. You have MES, traditional MES from the big companies like SAP, Oracle, and then of course, PTC, Dassault, Siemens, and others. And then you have this newer crop of MES solutions that are called additive MES from companies like AMFG, 3Your Mind, Link3D, Authentize, and others. And that's fantastic, because if the industry is going to grow, we need to have those applications that understand the unique differences between additive manufacturing workflows and more traditional serial manufacturing workflows. But there's still a huge gap that exists. And one of the areas that we're trying to focus on and bring our expertise from the 2D world to bear in the 3D and additive manufacturing world is around high order mix, super high volume workflows. And so in many ways, we're able to partner with all of the DDC members, as well as other companies, ISV software companies out there in the industry, to work together. I like to quote Martin Stoyer, and I know Harshil does as well, because he has really been at the forefront evangelizing additive manufacturing every event that he goes to. And something that he says consistently, and Martin Stoyer from EOS, by the way, a former Autodesker like myself, is he points out that we all have to work together. In the subtractive world, in the traditional manufacturing world, very rarely do you walk into a shop and see devices or machines from one company. And that's because it's just not realistic to build a business around one particular brand necessarily. And it's true for additive manufacturing as well. You have those processing devices and all of this. So Martin, when he points out that we all have to work together to bring additive manufacturing to the forefront, he's absolutely right. So we're committed to doing that, and doing that with as many of the DDC members as possible. So shifting gears from that real quick, I want to give you an update on the Universal Build Manager powered by Dyndrite. So as I mentioned, we're focused on applications to fill some of the gaps. And one of those gaps with this high order workflow, this very large volume orders of 1 or 2 workflows, is that we needed an engine that was going to be capable of driving those kinds of volumes. And we did a lot of research into the technologies that existed. And the reality was that Dyndrite, as their kernel, was the perfect solution for us. It gave us the performance that we needed. It gave us the flexibility, universality that we would be able to work with all of these other DDC members, the major OEMs, the SLMs and EOS, Aconity, Ascentium, Aeon 3D. I don't want to leave anybody out, Stratasys, 3D Systems, everyone. We needed to have a universal application. That was number one. It had to be performant. We needed to be able to process tons of orders. We needed to be able to do it in a CAD neutral way. We're trying our best to put STL behind us and work directly with the native CAD files. That was important for us, and that was a nice feature of the Dyndrite kernel. But most importantly for us is, and if you want to know what direction we're heading in, it is the total automation. And so for us, the Dyndrite kernel, by default in the build prep and build management, you are creating Python scripts. So you are capturing the manufacturing intent as you're doing build prep. So for us, it was a great solution to build our application on top of. And so we announced it last fall. Dyndrite also had an event. We gave people an update. We were getting ready to start the beta, but we started working with customers and we started getting a lot of feedback, and we went back to the drawing board, and we are super happy that we did that, because we have really made some tremendous improvements that when we do go to beta in the very near future, that customers are going to be impressed. People are going to be impressed with what they see. So we are planning to do our launch in the fall. Hopefully we'll be able to meet face-to-face at both Rapid and Formnext. And then you guys will be able to see it there. And I didn't want to waste this opportunity giving another demo or having one of our guys, our head of additive, who's in the room with me, Philip Thomas, give a demo, because a lot of people have seen it. You can go back and look at the video. What I wanted to do was I wanted to come to a customer. We're here at Cobra MOTO, and I wanted to actually let somebody that's helping us develop our applications tell you about their business, how they got into additive, and a little bit about what we're doing together, maybe at the very end. So I want to introduce Sean Hilbert, who is the founder of Cobra MOTO and Cobra Aero. So thanks for having us. Yeah, appreciate it very much.
Thank you for coming here.
Cool. So his businesses are very, very interesting. And what I want to do before we talk about the business, and I want to run a quick little video, if we could, of Cobra MOTO. So if you guys can do that for us, and we'll come back and talk to Sean.
Cobra has an incredible legacy of winning at this level of racing over the past 25 years. In fact, almost every single amateur national championship at Loretta Lynn's has been won on somebody riding a Cobra. It's really an incredible legacy, and to see these kids now as adults that have made their way through the ranks and up into the pros. A good part of the starting line at a Supercross race these days is made out of Cobra kids that were our customers at one point in time. And the whole goal behind this motorcycle was to basically make sure that that legacy remains. We've got a brand new bike. It's brand new top to bottom, starting with all new forged wheels that have a new spoke pattern. They're lighter, they're stronger. The suspension is better. The ergonomics and the handling has been improved. Basically everything you need to go win a race, we've made sure that we made better this year.
I think we're good. Are we back? All right, excellent. Yeah, okay, all right, we're good. We're back, thanks. It's a cool video, and it's a longer video if you want to go to their website and check that out. We'll give you the URL later. But before we get started, why don't you tell us a little bit about yourself?
Yeah, so Cobra's a Michigan company. I grew up in Michigan, and a lot of my formative years as a kid, I raced motorcycles, but I also did other things. But I realized that all my friends who had parents in the auto industry, they were struggling. The auto industry was really struggling. The competition was coming in. We didn't know how to manufacture things as well as we should have during those days. The legacy of the Marshall Plan in Japan in particular is really starting to pay dividends. And that gave me a real big interest in manufacturing right off the bat. So I'm an engineer by training, and then worked several years at Ford Motor Company, both in the research labs there as well as in manufacturing. I spent some time on the plant floor, and then I took a break to go back to school. And during that time, I put some business plans together around what the future of a power sport company might look like, because that was my other than manufacturing, that was my core interest.
So you went from Ford to, how did you get to Cobra?
So wrote the business plan as I was at Ford, or, my evenings and weekends, shopped it around, went to the capital markets at the time. It was during the time of the dot-com bubble back in the late 90s. And so finding capital for a manufacturing company was almost impossible, but not impossible.
Right.
We found several groups that were really interested in our ideas. Basically, mass customization in the power sports market, which had really never been done before.
Sure.
And you can see where additive really fits well into that idea. So we gained investment. We actually, instead of a pure startup, we decided that there was a perfect target company that we could go purchase. They're relatively new. They found some nice white space in the marketplace, in the motorcycle marketplace.
Right.
And so we purchased them 2003, and that's where it started.
So you buy the company, you guys start, was it tough, or did you walk into a pretty healthy business and it just grew? Or
we walked into a great marketplace and a business that was a mess. So we spent several years kind of, recombobulating the product, recombobulating our market. But the good news was we had a good tailwind. We had a very healthy marketplace for our customers. The housing market during those early 2000s was strong. A lot of our customer base kind of comes from that.
Right.
Comes from that blue collar world.
Right.
And
now, did you manufacture your own parts back then?
Yeah, so good question. Yes and no. We had a couple of CNCs. We did the bare minimum. We did little round spacers and a couple other parts. But we were like a lot of other manufacturing companies during those days. We purchased stuff mostly from overseas, Southern Europe, Japan, Taiwan. Okay. And we were an assembler. We put stuff together.
Sure. So so you mentioned the housing market. Yeah. 2008 comes. What happens?
Everybody knows what happened. 2008.
What happened to you?
Yeah, what happened to us? It didn't happen immediately, but as you might imagine, the economic downturn, discretionary income went sideways for everybody. And buying expensive motorcycles for your kids is not something you do when you don't have any discretionary income.
Sure.
So we struggled. We managed to maintain. We went heavily into export markets. And then we sat down one day and figured, if we're going to keep our guys working, our men and women working, and we're going to maintain the agility that it took to figure out, what the marketplace is going to do, not next year, but next week.
Sure.
I mean, literally, we were week by week. We needed to in-source and home source a large variety of components. So that was really our first major transition as a company.
So you added more CNCs, more fabrication, everything, brought it back in-house.
Yep.
And how did you, so that's more traditional manufacturing, CNC machining, fabrication. Yep. How did you get into additive? What was your start in additive?
Yeah, so like most other companies in those days, additive was, how can we make a prototype a little bit faster, right? So we bought a small FDM machine, MakerBot at the time. Made a bunch of little parts, anything that required tactile feedback, right? Anything that was on the motorcycle that would interface with the rider, that we digitally, virtually, we just couldn't tell, is their boot gonna hit that? Does that feel good on your hand? Right. We made those parts, we tested them and very quickly iterated, got a lot of feedback. And boy, oh boy, it was like a, eye opener. Wow, this really works. It's good stuff.
So did you start to outsource? Did you go to more commercial applications with?
We did. So for prototypes, we pretty much kept stuff in house unless it was too big. Then obviously we had to look for service bureaus that had bigger build volumes and things like that.
Sure. So parts like these, you started to outsource these.
We did. We did.
To Proto Labs.
Proto Labs is a great example. So brokers like Xometry, maybe if Proto Labs, couldn't get us something fast enough. But yeah, we used a lot of different folks.
Did you see, now I know that you are a very agile company, your engineering background is like permeates everything that you guys do here in both businesses. When did you start to make the shift away from just using additive or relying on additive for prototyping and getting into more of the short run stuff, and why? Because I think it's a pretty interesting story.
Yeah, so the first short run thing we did was on the subtractive side. We built fixtures that could, change quickly in and out.
Right.
Kind of took a page out of Toyota's playbook, built a single minute exchange of die. We became students of that whole thing.
Right.
Quickly interchanging fixtures in and out so that we could do small, short batches subtractively. And that really set our mindset for where we needed to be in the future.
Sure. And you also machine molds for injection molded plates as well, right?
Yep.
Okay.
Yeah.
And now, just out of curiosity, did you bring the injection molding back to the States, or was that still done overseas for the most part?
No, we brought it back to the States during that period of time. So basically one part after another, we created the mold for it here,
Okay.
and then local sourced it.
All right, well, we have a couple things we want to show, but why don't you just briefly start off by talking about some of the parts here on the table. And I know there's a story to a number of them, as well as some bikes that we have over on the side of the room. Yeah.
Yeah, so I mean, the parts that you see on the table here, this basically, except for this old, this is kind of this is one of our very first FDM parts that we did. As you can see, this little cutout right here, this is one of those things where, back in 2010, 2011, the value of rapid prototyping was really, that was kind of really coming to the forefront during that period of time. And the ability to make that cutout just right was important for us, right? We basically did a bunch of different iterations, and that was clearance for a rider's boot because they were riding the bike, and we maybe made 10 of those before we hit on just the right shape.
So now did you do short runs as well with some of these when you were testing, beyond testing them out when you were trying to go to market?
Absolutely. Yeah. So the rest of what you see here are all MJF components built on the 5200 that we have in our facility.
Now, but not back then.
Not back then, right? These are current stuff.
Sure.
And what you see here is basically a kind of a smattering of packaging prototypes, looking for fit and finish, looking for tactile feedback. But the other thing you see, and this is a good example right here, is a part that we have really no intention to go into early production with an injection molded part. It's designed to be injection molded.
Right.
It's an open and shut, nice design that would be an relatively inexpensive mold, relatively quick mold to make.
Right.
But for timing purposes, we're going to be running these in MJF for probably the first year of production.
Okay, for your new bike. Now this part is really cool, and you told me a story about it. Why don't you talk about that? Yeah. And how you use that with that rapid iteration.
Yep. So this is a throttle controller for our new electric products. So we're undergoing not only a digital transformation in how we build our products, but we're undergoing an electrification transformation on a lot of our products, either full electrification in the sense of most of our motorcycle business. We see power plant over the next 10 years. On the aerospace side of things, there's still going to be endurance applications that require engines.
Oh, sure.
But probably hybridized engines, right? Engines that drive generators, that drive other things on the aircraft. So this particular component is you can't just go to the marketplace these days and buy a throttle. You can for an internal combustion engine throttle. There's probably 100 of these on the market. But for an electric throttle that requires dual redundant sensors and requires specific technology that we're developing, we need to develop these housings. We need to develop how the sensors mount, how the sensors interact with the throttle tube. And that takes a ton of iteration. Right. And so
we're getting feedback from the field, from the racers, from the mechanics and stuff like that.
Absolutely. And now by having our own equipment in-house, we're able to not turn that iterative loop into a 1 or 2 week process. It's a 1 or 2 day process.
Sure.
So we can really speed the cycle, speed the clock speed, so to speak, of our process.
Right. Well, let's do this because the story actually starts in the metals world, and we'll come to that when we talk about the aero business.
Yeah.
But why don't you take a minute and show the viewers the bikes. We've got a combustion, we've got an electric bike, super cool, and talk about some of the components and how additive allows you to be more agile in business.
Yeah, okay. Yeah. So just a quick overview of what you're looking at to my side here. These are bikes that haven't hit the market yet. In fact, one of the reasons you see kind of a camouflage on this top unit, this is the first time really the world has ever seen this unit. It's going to be a brand new 2022 model. We're going to launch in September, and we've been utilizing kind of in a very traditional sense, utilizing additive manufacturing to, again, take that clock speed way up of our product development cycle and produce a lot of different iterations on different parts. And just a couple of quick examples. So this is our CX65 bike. On the bottom here is going to be our first entry that's fully electrified. And there's some interesting stories about this bike that we'll go into in a minute. But I'm just going to focus on this panel. We have several MJF components on this bike that we're testing right now. The number plates, what we call the front fork guard, the side panels, even the pan that's underneath the seat is all quickly designed MJF components. And when you have parts that require, from our standpoint, require tactile feedback, and what I mean by tactile feedback is any sort of interface from the rider or even the mechanic. So what kind of shape does the seat pan need to be so that the rider feels more comfortable? This side panel is a great example. We've got two areas in particular that we did probably, I'm going to guess, at least a half dozen iterations to make sure that we were just perfect. And we can do those iterations, within a 2 or 3 week period, because every day we would receive feedback from the field, do a quick redesign, and then hit the print button and go back at it again. So this hole right here is actually an access port for adjustability for our rear suspension. And it might seem pretty simple. You just put a hole in the side panel, but in reality, that hole has to be lined up just perfectly so that the tool that does the adjustment, can be fed in properly. But the other thing is that the socket is way in there; it's kind of dark, and the user has to be able to see the fastener that they're aiming for. And so, just the shape and the size and the angle of that hole took 3 or 4 quick iterations. And in the past, we would have taken a good guess and run with it, and it probably wouldn't have been right. This angle right here, if you can see it, you can see that the stickers are kind of messed up a little bit on the bottom of the panel. And that's because that's where the rider grips the bike. And the shape of this, as their boot grips that bike, we don't want any sharp corners. We don't want the boot to catch anywhere. We want the rider to have a nice smooth transition fore and aft on the motorcycle, because they move around on the bike a lot. And so just the angle of that, we've probably changed 3 or 4 times. And those are the kind of things that we can do to really push the development to a much faster speed than we could otherwise. Again, super traditional, right? Where all of these parts are designed for higher volume, at least current higher volume production techniques like injection molding, but we're using additive to speed up the clock speed. A little bit different on our new electric motorcycle. That bike is going to go to production in Q1 of 22. It's going to be a 22 model as well, but there's going to be a lot of parts on this bike that end up in MJF to begin with, and that's really to meet launch timing, and we can talk about that in a minute.
Yeah, sure.
But there's a big in this side of the business, on the motor side of the business, launch timing is everything, as you can imagine. New model years come out, and if you don't hit that, then you basically lose all that time in production until the next model year comes around. So if we lose a month, it's not just being a month late. We've lost that production window.
Whole season.
We could lose the whole season if we're not careful. So anyway, that's a quick overview. Really fun new products that we have coming out, and additive has been a key part of the development process. I'll even show you. This is the battery pack down here. We had enough build volume, just barely, within our Renishaw AM400 to print the entire battery housing at one point. That's a cast part eventually, but but we were able to really get there much quicker by using our additive capabilities.
Very cool. Yeah, and so this is an MJF build of just the housing, because you also were testing some of these component parts as well. And you even said that some of these you're probably these are not just prototypes, you're going to go into production with these as well.
Absolutely. So, you've got things like battery covers, bezels, more covers up here. Internally to the battery, you can't even see it, but the array that actually holds all the cells in place while they're being actually right after they're welded. Okay. Those are all going to be additive parts. And I don't foresee, I guess here's what the future looks like. We, as you mentioned earlier, we make all of our injection molds in-house. We've got one mold maker. We're a small company. We're under 50 people. So we have one mold maker that's going to make this mold, and then he'll make this mold, and then he'll make this mold, and then he'll make that mold. And so I mentioned how important launch timing is. Well, we don't have to wait for him to finish every mold anymore. We can literally get to production when we say we're going to get to production, and prioritize what I would call cost reductions or cost thrifting over time. Yeah, okay, this part in the long run probably should be an injection molded part, at least in the next foreseeable future, right? Maybe in 10 years, we wouldn't even think about building a mold for this part, but now we will. It's a few pennies to make in an injection mold process, but we're never going to let that delay our launch timing ever again. Right,
so you mentioned the metals, and so what I want to do is I want to shift gears and talk about your other business called Cobra Aero. And before we do that, let's run another quick little video to give the viewers an idea about that business. All right, we're back. Thank you. We did a quick change during the video, and we've got some parts up here from Cobra Aero. And so let's see, we talked about you really got into commercial additive with metals first. So we need to go all the way back. So you have Cobra MOTO. And you deal with that lean transformation 1.0. And then how did you get into the aerospace business?
By brute force and awkwardness, maybe. I don't know. We came to the realization at one point that in the middle of the economic downturn, that was probably about 2010, 2011 for us. Things got delayed a little bit, in terms of when our market really hit rock bottom. But we came to the conclusion pretty quickly that we needed to look for adjacent marketplaces that could utilize the great folks we had, the great equipment we had. Basically, were there any core technologies that we were really, really good at that other markets needed?
So did you just came up with this idea, or did you have somebody approach you with a problem, or how did it work?
Yeah. So the first I thought about doing small engines for drone aircraft, and keep in mind, right about that time we were what, almost a decade, maybe a little over a decade into the conflicts, in Afghanistan and Iraq, and you're just starting to hear about these things called UAVs on the news. drone aircraft, some people are calling them. And the reality is that from about 2002 on, our soldiers were using really small aircraft in the Middle East to basically be eyes in the sky for them.
Right.
To look over the next, three streets over in Fallujah, or the next hill or whatever. They're looking for. They're just trying to be safe, right? They're trying to protect themselves. And the problem is that these aircraft got rushed into that use case so quickly, that I visited a company in Hood River, Oregon called InSitu. They were kind of the first big players on the UAS market. And I met a general there that was there for a visit, and he said, I've got a $250,000 camera on one end of the aircraft, and I've got a piece of junk hobby engine that I can buy at the local hobby store on the other end, and I'm losing $1 million in cameras every month. I need a better engine. And so that was like, that was it. That was the spark that really got us going.
So when you started out, did you start with additive from the very beginning with that business, or what?
We didn't. We really started with we started. I would call it additive light. We were a lot of our prototyping, especially for engine components, were cast. They were rapid casts, so they used they used some additives in the process. The cores and things like that were printed.
Okay, awesome. And I've noticed this, and I'll tell you, the video is not going to do this justice. It is a work of art, and a lot of the components on here. So, and we can't zoom in, but I do want you to talk about some of the pieces on here, the cowling, some of these pieces now for mounts, engine mounts to the fuselage. And this is a pusher, so it's in the back of the drone, the back of the UAV or SUAV, and it pushes the plane. But you have these incredible mounts. These are titanium printed on a Renishaw printer, which is your very first printer, right?
It is. And Renishaw AM400.
Now, were these generatively designed at all, or were they just sort of, do you guys do it yourself, like manually?
We did a little bit of kind of pre-generative, a bit more topologically optimized stuff. It wasn't, I wouldn't call it a pure generative design, but it's certainly optimized. Okay, sure. But so tell us a story. How did you get into the Renishaw printer? So we knew kind of early on that we had a couple of choices in front of us. We could tool up for parts like this, which severely limited our flexibility, right? As you well know, that's a beautiful part about additive. And it also took a tremendous amount of time to get where we needed to be. And I had a conversation with one of our customers one day, and he's like, if you were to build an engine frame, wouldn't it be really cool to integrate, these three parts? And if you did it additively, you could do that. I'm like, wow, that's really cool. So immediately we started conversations. Went to Chicago, visited the folks at Renishaw. They were awesome. Really helped out a lot in terms of strategically what direction should we go forward. Should we rely on service bureaus? Should we pull capacity in house? And it took us about a short 3 or 4 months to make the decision that, we're going to dive in. We're going to dive in and make, this digital transformation, really. That we needed to make to move us to the next level. So almost from the very beginning, you started to move and think about designing the parts specifically for additive. And this mount is a great example. So we have 3 competitors' mounts in back. This whole mount weighs just over 100 grams. It's featherweight. The lightest competitor mount out there for this class of engine is about 380 grams. And if it weren't for, and not only that, we've integrated several parts into the mount itself. So it's not just a mount, it's a mount, it's a servo mount here. It does a lot of things that the traditional mounts don't do. Exactly. And not only that, it's either you put more fuel in the UAV, or you have to shorten your mission time, because you can't be in there as long, obviously. So this extends mission time or lightens the weight, and just saves the fuel and improves speed and things like that. Talk about that part. It's so really cool. This is the cowls. This actually cools the engine. The engines at this point in time anyway are air cooled. We've got some incredibly cool designs that we're working on right now that are liquid cooled as well. But this is a great example of a part, and that's a key distinction really between the aero business and the moto business. I mentioned before, everything we're designing is around the capability to be injection molded, right? We want to make an open shut mold, maybe a can here and there to get rid of a locked in part, but really everything is with we're gonna
ultimately you're gonna go to
higher
traditional
margin.
manufacturing. Yeah.
Just the opposite for aero.
Okay.
We realize it's a different marketplace, different margins. So costs can be a little bit higher. So we dove in right off the bat with design for additive.
High margin, high value parts.
High margin, high value. So what can we do with additive from the design standpoint you could never, ever do with any other manufacturing technology?
Sure.
And if you pretty much everything you look at on this engine that's additive, and that includes the exhaust system, the cowling, the engine cylinder, the cylinder head, the mount, the intake manifold, a lot of the linkage systems that are controlling all this stuff. I mean, about 60% of this engine is additively manufactured. And every single part that is additive is designed to be forever additive.
To leverage the benefits of additive as well. Not only in part component count production or count, but also in the actual performance of the part as well. Now there's a part, and I know they can't see it. I'm going to try and move this around. It's always dangerous during a live event. And I know we can't zoom, but this exhaust component here is absolutely amazing. And I know you have, is there a story here? Is that like an older traditional design and an updated?
Yep. So this is our subtractively bolted together machined part. It's got 13 different components. It's, as you can tell, it's very friendly for subtractive manufacturing, right? A lot of right angles, a lot of,
2.5 axis.
2.5 axis stuff that's going on. It's heavy. It weighs about 150 grams more than the additive part. And as you can see, the additive part, we've kind of, this is angled. I don't know if you can see it on the screen or not, but this part is angled into the nose cone or the spinner, we call it, on the aircraft, and that helps the airplane cowl better, so it's more aerodynamic. And it also helps the propeller be more efficient because you're masking less of the prop. So
and even the airflow is matched to the radius of the spinner as well.
Yeah, exactly. So huge improvements designing for additive manufacturing, and that's not where this ends. Where we're going is we've got a contract with Air Force Research right now, and the name of our what's called an STTR is using additively manufactured novel shapes to help attenuate sound. So we're this outlet right here, what goes inside of the muffler is actually going to be the only way you could ever make it would be additively manufactured. It's probably going to be, it's going to use lattice structures and things like that are very complicated, but they follow the additive paradox, right? And that is sometimes the more complicated a part is, the easier it is to print. And so things that you could never do subtractively or any other way for that matter, we're going to be doing on this aircraft engine within a few years.
Sure. And, for full disclosure, we were originally contacted for your metal printer. We had someone that saw the announcement and a former Renishaller, we'll say, and they reached out. And you were interested in doing some testing as well for the application. And we were obviously looking for people to help us, and then found out that you guys were in the midst of considering purchasing an MJF printer to go along with the Renishaw printer, an HP printer, 5200 series printer, to bring that in-house. And I remember talking to you about it because we were interested in working with somebody that had multiple machines from multiple manufacturers, multiple processes, especially around metals. HP is doing some metal stuff, but they're not as far along as the other guys. Obviously, the big ones, SLM, EOS, X1, etc. Renishaw has been around forever in the business, and so we were eager to work with you and your team to figure out, because it's one thing having an idea about solving these problems. And even though we're going after traditionally a different type of business for the larger application, the engine has to be robust enough to be able to deal with all of these parts and all the different materials. So we started working together before you even got your HP printer.
Right.
And so today we're working with you, and you're using Renishaw QuantAM software as well, to do some of the tool pathing and things like that, while we're doing our testing and evolution on things. So that's been great for us and our teams working with your guys on that, because again, at the end of the day, even though traditionally, we would go focus on like the really high-end, high value, very sophisticated, very large parts. Some of the manufacturers, OEMs, they have build volumes that are a meter in size, right? Which is larger than both of your machines.
Right.
And so the amount of data that we're dealing with, it just increases astronomically. And that's something that Harshil talks about. He's been talking about it for years, and we're getting to that point right now. And so I know that that's the more and more sophisticated parts you guys are designing, the lightweighting, especially some of the insides of some of your engine components, means there's a ton of surfaces, lots of voxels that we have to be able to process, and you need to be able to do it very quickly. And in your case, it's because a race is coming up. We're talking about you have a race in the weekend and you want to come up with, I don't have it anymore, but that throttle body assembly. Well, you want to have 3 designs and you want them all tested out and you want to get feedback, or you have that side panel and a mechanic requested, you send it out. Is this what you're looking for? Is this going to work? You have to be able to process those builds very quickly for both metals and plastics as well. One of the things that
I call that, creating at the speed of thought, right?
Right.
When we think of something with modern CAD tools, you can create the digital design very quickly,
right?
But then being able to actually create the physical part almost as quickly or quicker,
Right.
That whole process, compressing that timeline is incredibly important.
Sure. And so for our relationship, it's more about pressure testing the engine for our solution and making sure that it's robust enough, because typically we go after the customized, personalized, on-demand, known part. Even though there's modifications to it, there's texturing, there's labeling, things like that. It's not quite like the service bureau type of an application where they may get an order for 10 of these mounts in the morning, and they've got an order for 25 of these, by the afternoon. So it's really interesting. And of course, one of the things that we've talked about too is that there's product development, process development, and production. And our emphasis is focusing on a certain type of production business model. When we talked about this, and you mentioned when we made our announcement, a lot of people ask, because we have a lot of partnerships with Siemens and Autodesk, Materialize, and one of the questions was, and of course now Link 3D and AMFG in the additive MES space, and people are like, well, what are you guys doing? And it's like, well, we didn't set out to compete head to head with those guys. We didn't set out to create a category killer with our engine. We set out to create a new category altogether. But again, at the end of the day, it has to be robust enough to deal with all these real world parts. It's even though we've sort of we've picked a really interesting business and market segment to go after. The reality is that even those other MES systems are going to need a tool if they start getting into higher volumes of production to be able to support parts like this. You mentioned that one of the big differences between MOTO and Aero was the fact that you're designing your parts to be thrifted or for eventually to go to full scale production with traditional injection molding and CNC machining and stuff like that.
For now.
For now, right? Yeah. Exactly. Well, of course, the costs are always going to come down with additives, so it is going to be interesting to see where that transition starts to happen, if it starts to happen too. So one of the things that you talked about was how your business has evolved, and you call it, I mentioned the lean transition or lean transformation 1.0. You started to go into the lean transition or transformation 2.0 when you got your first, what I call commercial industrial 3D printer, which is the Renishaw. Right. Should be pointing to metal parts here. The Renishaw printer. How do you see your the next steps for these businesses evolving using additive?
Yeah, so lean transition 1.0 still required that we had a deep supply base, and we still have 150. Sure. We have 150 global suppliers. We've got one purchasing and logistics person.
Right.
And that's an incredible amount of complexity in a supply chain to handle with a very small staff. And so we're always looking for a way, how can we de-risk the supply chain? How can we bring things closer to home? How can we have, as I've been saying for a decade, how the heck can we control our own destiny in more than one way? And I can give you story after story about parts that were, left on a boat and ended up going around the.
Wait, hold on. You had a container that was stuck on the Evergreen ship in the Suez Canal. Was that?
We still haven't got. We saw the manifest.
Oh,
And
okay.
it looks like it's there. We still don't have the parts, and we don't know yet. That's the perfect example of supply chain risk for us, right?
Yeah.
So
that was funny.
that a more very real world, closer to home thing that we have going on right now is our castings.
Yeah.
So we've got a local casting company that is 21 weeks, lead time, which was 8 weeks a couple weeks ago. And that's the,
sure.
When you look at our MRP system and it says 8 weeks lead time and everything's driven off that MRP, and you send the PO and then they say, oh, no, you're gonna have to wait till September now.
Right.
Those kind of disruptions just blow our business to pieces. So we have to figure out ways to bring things closer to home.
Sure.
And luckily for the aerospace side of things, we can go literally 1 4-inch wall away from our lunchroom and make more, castings.
Right. No,
It's crazy to think how clean and how lean that is, but that's what we're doing.
Yeah, it's impressive. And your operation, I know we didn't have time, and logistically, hopefully we'll be able to do a video to do you guys more justice as far as the production end of things. But it's very impressive to see how quickly, even on the plastic side, you're able to stand that part of the business up. And I mentioned that for us, when working with you and with Renishaw, with the Quantum software, our key focus for the UBM right now is number one, compatibility. We know all the features that we need to be able to support for the types of applications that we're going after. But we need to make sure that, first of all, we're compatible with all these different devices that are out there. And again, I would really appreciate all the help and feedback that you're able to provide, and validation that you're able to provide, and working with some other people as well with some different types of processes. But interoperability is the next step, and that is working more closely with some of the applications from folks out there that are used to specifically drive their particular machine types. And that was one of the other aspects that we were, when we selected Dyndrite as the core technology inside of our UBM, Universal Build Manager, it was because of this plugin architecture that we have. And so we're working with a lot of people right now because the IP, the secret sauce from all these OEMs, they're certainly not going to give it to HP, and they don't want to give it to anyone else either. And so for us, having this plugin architecture allows them to not have the risk of exposing their IP or losing any control over their IP, but still at the same time, we're able to have a more seamless integration with their devices, and it's one interface, which is great. And that's what everybody's looking for. And it's not entirely new, but it's certainly one of the key pillars, if you will, of our application. We know we need to be able to do that. And we don't want somebody to have to go out of one application to go into another to do it. This is something you guys have talked about as well. It's like, it's a hassle and it's a waste of time. And when you're training new employees, this is another thing around the automation. And this is what I wanted to sort of end our little discussion about, was on this focus of automation. There's 2 levels of automation. There's the factory industrial automation, like robotics and making your operations more efficient. But then there's the software automation side of things. So why don't you talk a little bit about that?
Yeah, no, and that's really important for us going forward, right? Our best and brightest right now are spending a lot of time, putting builds together, right? Making sure that things are oriented just right, making sure that we've got, parameters set properly, making sure that if we need to on the metal side, that things are supported the way they need to be supported. Lots of kind of just grunt mental capital is going into each build.
Sure.
And the more that we can streamline that process, and the more that, the 2 things that we really look forward to are automation around orientation and automation around serialization.
Oh, and traceability. Yes,
and traceability is huge. We want to know, we want there to be a number on this part. We want to know where in the build chamber it was built. We want to store the metadata around laser parameters and things like that. Maybe some feedback, temperatures and things like that.
Sure.
But we want to be able to have all that information at our disposal down the road for full traceability. And not only that,
And it has to be automatic.
it has to be automatic. Right?
Risk getting the wrong serial number, the wrong number on a part. It's
You mentioned lean 2.0. Maybe lean 3.0 is us determining what set of parts we need 3 days from now.
sure. Yeah.
And pulling that, a pure lean pull system, pulling those 28 different parts together, kind of like a service bureau would do, except we need to have serialization, we need to have full traceability, and we need to know exactly the orientation this thing is going to be built in every time, so that we have the material properties and the structural properties that we think we are designing into the part.
Exactly.
And we can't have a human being doing that every single time.
Exactly. So it's not only the knowledge about how you're manufacturing the parts, it's also making sure that you are de-risking the manufacturing process as well. Because again, in aerospace, you can't afford to make one mistake. You just can't do it. So what I want to do is, I know we're at almost at the top of the hour. And I know folks are getting ready to go to lunch out there, so it might get a little bit noisy. Might be a perfect time to switch over to the Q&A session. Sure. Before I do that, thank you so much for having us out here.
Yeah, thank you.
The products are amazing. They're awesome. And the website for Cobra Moto, what is that?
So just cobramoto.com, easy to find. And then Cobra Aero is cobra-aero.com.
Gotcha, awesome. So let's go back to Kristen and see if she has any questions for us in the remaining time that we have.
Yeah, hi guys. That was really interesting. Love seeing all those parts. I think that's something that people are always interested in seeing, the real applications of these things. We have a couple questions. One of the questions was from very early on in your presentation, Anthony, and you mentioned super high workflows. Univolumes have always been an issue with additive manufacturing. With the innovations that you're seeing coming into play, what kind of volumes do you expect to see maybe in 5 years, 10 years from now? What kind of advances are we going to make in that specific arena?
Well, so it's an interesting question, and we may get into this in the panel later, but the way I look at it is this. There are parts, for example, that Sean is never going to make more than 50 of, because it just doesn't make sense. If you're going to make 1,000 parts, you're going to injection mold them potentially. For this business, you may make 2 prototypes, or excuse me, you may never go away from additive. So from a volume standpoint, if you scale that up to different types of applications, there will be automotive and aerospace applications where you're going to start seeing larger and larger and larger volumes. I mean, we've already seen it. I mean, high volume production is happening in almost every industry. So it's not like it isn't happening. It's just not happening enough. And that's because the evolution of the technology and the processes and the printers and all of these different things and the materials, the material development has been moving at such a pace that, from what I've heard from people, the engineers are like, look, we would like to move more parts to additive, but we're trying to let the dust settle a little bit. And I think some of the big innovations we've seen over the last year, just like with SLM's 12 laser machine and stuff like that, those are the kinds of things where people are going to start making a jump, getting more parts on their printers. But there's 2 aspects of high volume. There's high part volume and there's high order volume. And our expertise inside of HP is around high order volume type production and automated workflows. And so we're going to spend a lot of time focused on that. Whereas the other companies, we're letting them stick with that part development, process development, and production side of things, where hopefully their customers are going to start making 10,000, 50,000, 100,000 of more parts. So I would say the volumes are going to go up in 2 areas. One, as materials and the science behind additive starts to stabilize a little bit more than it has prior, you're going to start seeing the volumes jump for the same part. For customization, personalization, on-demand manufacturing, it is the people that are starting their businesses, I call them born additive, and they say, I'm never, like, this is gonna be an additive part. I'm never going to, or maybe you couldn't injection mold this as one part. I'm only gonna produce it, but I need a different serial number, or maybe I have to adjust the size of some of the features of a part, or it could even be consumer type products where you're putting your name on it, or a saying, or a texture. So you have similar parts, but they're only, or you could even say families of parts. You're just making many, many, many. So you're getting lots of orders of one, as opposed to one order with many, many, many parts. So I think it's just going to be, as people start to mentally make the shift over, that additive manufacturing is affordable, and it's becoming more and more affordable. We'll see the volumes on both sides starting to go up. I hope I answered your question.
Yeah, I think so. I mean, I think one thing, just real quickly, if you could clarify, is, you know, when you refer to high part volume versus high order volume, kind of what the difference is there and why they're different.
Well, it's just that. I mean, for example, well, I don't have my phone. I turn my phone off for once in 6 months. So we have a phone over here. A phone case is a perfect example. I don't know why there aren't 500 businesses out there making custom phone cases out of plastic materials. They could even be metals as well. But you have a phone case, and you have your Galaxy phones and your iPhones and the sizes. But then most people, they want a personalized phone case. They want to be able to put their name on it. The beauty about additive is it doesn't cost any more to put somebody's name on a phone case. It doesn't cost any more to change the texture. It doesn't take an extra 20 minutes to machine a texture. You're just literally printing it. As they say, there's no penalty for complexity. As long as you have the tools, there's no penalty for complexity. So that's going to drive a lot of the personalization of one. I only need one phone case, right? I don't need 10,000 phone cases, but if I start a business making phone cases, I want to make 10,000 of these a day if I can. Now, if I'm an automotive company, I'm going to make 50,000 of a part. So that's one part, 50,000 high part volume, right? They call it high volume, low mix versus high volume, high mix. Even if that high mix is just literally the difference between a name that gets printed on the back of a phone case. You think about it in the fashion industry and apparel industry, Vans shoes, Nike ID, Oakley. I mean, the future is personalized, customized, and on demand. That's what we believe for a huge market of businesses that haven't even started yet, but will, because they'll be able to take advantage of additive to produce those parts.
Got it. That makes perfect sense. Sean, we got a bit of a different direction here. Sean, it appears that your specific market, specifically, it looks like with Cobra MOTO, might not be as regulated as traditional automotive applications. Are you seeing any hurdles regarding regulations with regards to that, the AM parts in that business?
With regard to the AM parts, I think so. The big picture answer is absolutely yes. We're fairly unregulated now in the sense that the federal vehicle standards don't apply to us because we're a race machine. EPA requirements don't apply to us because we're closed course competition. So we're lucky in that regard. As a small volume producer, if we did have that kind of regulation, honestly, we wouldn't be in existence. However, there are entire countries right now, Belgium is a good example, that have put a horizon out there, maybe 10 years, maybe 5 years, to say, listen, there are 0 internal combustion engines that are going to be sold into these countries in that time frame. And so that's the big part of I mentioned earlier, we kind of have 2 major transformations going on right now. One is the digital transformation in manufacturing, but we also have the electrification transformation in our propulsion systems. And additive is going to play a big role. It already has played a big role in that. And indeed, we're going to be going to series production with additive parts in our battery cases, on our motors, on our electronics that are all additively made.
Cool, very cool.
Cool.
Sean, any plans to move into a third Cobra business?
Top secret.
I hope not. For my sanity, I hope not. No, there are lots of ideas out there. But here's our rule. They have to be 4 letters. So it's MOTO, Aero. So whatever you think of, it has to be 4 letters.
Fair enough.
Interesting. Yeah.
I think to wrap up the Q&A, Anthony, what were your key motivations, or what was you and your team's key motivations to develop the software that you've been alluding to? It's going to be launched in the fall.
Well, it's a very practical. Here's a reality, and I've had some very frank conversations with people in this industry about this that ask why we are doing what we're doing, and I answered it directly. If the tools existed to push all the different business models for production, HP would be selling a lot more printers. EOS would be selling a lot more printers. Stratasys would be selling a lot more printers. Aconity, Ascentium, everybody, 3D Systems, everybody would be selling a lot more printers. What is one of the bottlenecks to mass adoption of additive manufacturing? It's not the materials, it's not the devices. In many cases, it's the software, and the software is evolving. But in many cases, it's evolving in certain areas, and while whole other areas have been ignored. And there's reasons for that. There's business reasons for that. If I have 20,000 customers, 50,000 customers, I have to focus on the needs of those customers. And when those customers are running traditional businesses with traditional business models, that is where my focus is going to go. I don't have the luxury, particularly for smaller companies that are growing over a decade or two, to automatically shift gears and stand up a whole nother business. It doesn't happen. At HP, it was, hey, listen, while we see this opportunity for HP, we recognize that HP is only going to be able to benefit from a small segment of that opportunity. If HP releases universal products, we open up the market opportunity for HP to sell these solutions regardless of what print application or process or material customers choose. Customers are going to choose the right printer with the right material for their application. Nobody is going to change that. HP recognizes it. Other companies in the past have recognized that when it comes to CAD, CAM, and simulation and all these other applications. So that's our motivation. Our motivation is to create these tools so that we all of our companies together sell more printers. And if we do that, and additive manufacturing starts to reach the potential it should have, folks like Martin Stoyer won't be the only people out there ringing the bell by themselves. It won't have to, because everybody will have adopted additive manufacturing. That is our goal. We measure our success by the printer sales across the entire industry. So thank you for that question.
I think that's really interesting, and the one thing that I want to reiterate, is that it's a universal solution. So it's intended to be on all printers to advance the industry as a whole, which I think we're all, everyone can get on board, obviously, with that.
Yeah.
I think, as well as it reminds me of one thing that Harshil said yesterday, or multiple times he said it yesterday, is, it really boils down to the fact that hardware is outpacing the software, and it's time that we address that, because we're gonna get this big divide if we don't sooner than later.
And the business models have outpaced the software as well. So that's what we're trying to solve.
Cool. Well, thanks, guys. This is awesome. Do you have any closing words before we move on?
Look, we are going to have a beta coming up, so I just encourage people to go to, the quickest way to get there would be to go to the URL dyndrite.com/HPUBM, and they can apply to take part and participate in the beta that we'll have coming up. And hopefully we're scheduled right now. My team is going to be in the Dyndrite booth at AMUG. With the way things are going with COVID, it could change. But if you are planning to go to AMUG, please come by the Dyndrite booth and say hi to myself and Philip and Jen. Behind the scenes, we'll all be there. And we would love to meet you and get your feedback. And if you're interested in becoming a partner of ours like Cobra and helping us in the development of our software applications, then you can reach out, shoot me an email because I don't have any other better way for you to contact me. Anthony.graves@hp.com, Anthony.graves@hp.com, and we'll chat. So thank you, Kristen, so much. Thank you, Harshil. Thank you, Dyndrite, and looking forward to the rest of the. I got to thank Sean. Thanks, Sean. Yeah, of course, I have to thank you, Sean. But we're looking forward to the rest of the event today, and we'll see you guys hopefully in Florida in 2 weeks. So cool. Thank you.
Great. Thanks, Anthony. I'll see you there for sure. I'm looking forward to it. All right. So up next we have Sean Young from NVIDIA.
Thanks, Kristen, and thanks, Dyndrite, for having me here. And clearly, I drew the short straw, having to follow Anthony Graves. So I don't recommend you do that if you have the choice. But Sean and Anthony, that was a great presentation. So I'm Sean Young, Director of Business Development for Manufacturing and Visualization Spaces at NVIDIA. And I'm going to tell you a little bit about what we're doing with Dyndrite. And there's a lot to tell. Hopefully you see my screen. So in case you're not aware of NVIDIA, our business is accelerating compute across a variety of vertical industries. You may know us from our acceleration of graphics for games, but our business extends far beyond that. We are powering the Da Vincis of our time, and we're the driving force behind compute for artificial intelligence. Our software development kits, SDKs, are used by millions of developers worldwide, including Dyndrite, who are using our SDKs for their applications, and others are using our SDKs for their world-changing applications as well. So let's talk a little bit about how Dyndrite uses our SDKs. Dyndrite leverages our NVIDIA CUDA SDK to develop their application, and our related HPC SDKs to build advanced compute capability. NVIDIA CUDA is our common SDK, which means that software written for CUDA can run across our entire range of GPUs. And CUDA taps into the capability of the GPU to deliver accelerated computing performance inside of the software, in addition to graphics and other things. Our hardware is quite impressive, and together with NVIDIA CUDA SDK, our GPUs power many of the top supercomputers in the world, including the Summit, which you can see on this slide, which is actually the fastest supercomputer in the world, powered by NVIDIA. And that brings us to the world of 3D printing. And in 3D printing, I believe you're all seeing that the growth of slice files is accelerating quite rapidly, so rapidly that you might actually need a supercomputer to process all that information someday. The good news is that NVIDIA and Dyndrite have partnered to help you with this problem. A word of warning and some background onto why Dyndrite chose to build on the GPU. These problems are not really built for the CPU. So Dyndrite requires a GPU. I just want to make sure that's clear. And the reason why they chose the GPU, the problem with the CPU is that it doesn't scale like it used to. Moore's law, as you can see by the blue line on this chart, that's the CPU scaling, that has been known as Moore's law. That's kind of tapered off in a pretty significant way. And CPUs are no longer delivering the year-over-year price performance value for compute that they used to. But if you look at the green line, that's NVIDIA GPU. There's no GPU law, but the media like to say Huang's law. Jensen Huang is our CEO, and you can see that our ability to scale, or what I like to think of as hyper-parallelization, that's just starting to take off. And it's just year over year delivering incredible linear gains. And there's a reason for that. It's because GPUs are really good at computing thousands of small jobs. We have all these little cores in the GPU, and you could send pieces of the job into those little cores, and they all get computed in parallel. Where CPUs, a single CPU might have 64 cores. Our GPUs have thousands and thousands of cores, and they all get very linear scaling. So that brings down the total cost of ownership compared to a CPU. CPUs would be too slow, so you would have to add more and more CPU servers. All those servers take up physical space, electricity, power for cooling. So it just costs a lot to scale on the CPU compared to the GPU, which is because you get so much performance on just a single GPU, you need a much smaller physical space, and the total cost of ownership is therefore much lower. And so net, the things you can do with Dyndrite just would not be realistic to do in a CPU, which is why Dyndrite chose a GPU. And here you can see a little bit of the gen over gen performance. I mentioned earlier that our parallel computing performance is really just starting to take off. And here's an example of the RTX Quadro 5000, which started off with 4.25 gigaflops in just a couple of releases ago. And now in its current generation, A5000, which we just announced last week, there's 28 gigaflops. So that's a 6.5x performance gain in just a few generations. And this is the GPU, by the way, that I recommend that you use with Dyndrite. And it's available as you see it for the desktop workstation, but also it's available in a mobile form factor for mobile workstations. So now let's take this idea and scale it out beyond a single workstation to this idea of a digital front end, which is a concept for deploying compute for 3D printing. So a digital front end is a dedicated computer that queues jobs and accelerates the processing of large data sets. If you're familiar with high performance compute, also known as HPC, or 2D printing RIP, a raster image processor, this should be a very familiar concept. The digital front end offloads the data prep from both end users and from the machines, the 3D printers. And therefore, it simplifies fleet deployment and allows you to scale on the machine side without having to worry about where the compute's coming from, because it's all managed centrally, not on the workstation, not on the printer necessarily, but we'll get to that, but in the central front end, the digital front end. So option one for the digital front end in terms of deployment is just what I just described, to use a central server, and this server processes Dyndrite data, which is then sent directly to the onboard controller on the machine. Option number two is to bypass the central server and instead have the GPU-enabled workstation directly connected to the 3D printer controller. So this is a more affordable option that might be well suited for standalone machines. And option three is a bit more sophisticated. NVIDIA is able to help machine vendors design a custom embedded GPU specifically to meet their needs. This solution might be desired for on-process modeling use cases, where on-device process modeling use cases, where I/O and processing latency might eliminate other options. For example, if you wanted to do some real-time simulation based on the data coming from the machine and from the output of the machine, and you wanted that data to inform the next run, then you might want to have onboard compute capability that wasn't hampered by the bus, by the networking or network protocols or infrastructure, directly connected through the motherboard from the GPU compute to the machine controller. So that's getting into some sophisticated use cases, but NVIDIA can help machine vendors design these embedded chips. So it's likely that the best solution is a combination of all of these options. The good news is that all of our technology, all the technology that I've talked about so far is highly modular and adaptable, so you can mix and match and you can scale as you grow. So in conclusion, I strongly suggest that Dyndrite users run the current RTX A5000 GPU in their workstation or mobile workstation for setting up the jobs with Dyndrite. Then for scaling out a digital front end, there are a number of options depending on your needs. You can deploy a centralized GPU server. You can attach a workstation with GPUs directly to the machine, or machine vendors can even work with NVIDIA to build custom embedded NVIDIA GPUs in the machines. I know that this can all be a little overwhelming, so please reach out directly to me or to the team at Dyndrite to get advice. And my email address is seyoung@nvidia.com. So that's it for me. Thank you so much, Dyndrite team, for having me here, and let's turn it over to your questions.
Thanks, Sean. We do have a few really good questions here. First one is, does NVIDIA and Dyndrite see any impact on plans due to the general GPU shortage currently going on? And is that likely to last into 2022, 2023?
Yeah, well, in fact, there's when it comes to GPUs, there's not a general shortage. There's a tightness of supply in some of our GPU models, especially on the consumer side. And there could be tightness in supply on some of the enterprise models, but it really depends what you need. So I don't see our supply issues getting in the way of our ability to deliver. We worked closely with our OEM partners who actually incorporate our GPUs into their servers and workstations to ensure a steady supply for the machines they sell.
Great. Another question is, you mentioned massive productivity gains. What is the cost in terms of electrical power and more advanced cooling required for such gains?
Well, that's just it. Yeah, at NVIDIA, we have a saying from our CEO: the more you buy, the more you save. And because of the compactness of our solution, in some cases, on the rendering side, we have one GPU server replacing 36 CPU servers. So in that case, the total savings over 5 years for replacing 36 servers with one GPU server, that's $575,000 over 5 years. Because of the compactness of the solution of the GPU compared to the CPU, and again, I'm not talking about the chip, I'm talking about the chassis, because you only can fit so many CPUs in a chassis. So you need to add nodes of CPUs. The more nodes you add, the more money you have to pay for power and cooling. And so if you compare 36 CPU servers to one GPU server, you're just going to save a lot of money.
Great. So a couple times you've mentioned the different solutions for mobile workstation versus desktop workstation. Can you go into a bit more detail on the difference between the two?
Well, the primary difference between the two is size. I mean, I think that's kind of obvious, but the amount of engineering work that goes into the desktop and mobile, actually there's probably more engineering work that goes into the mobile, because it's just so hard to get all of that power and performance into a small form factor that doesn't overheat. The main difference, so for example, I mentioned the NVIDIA RTX A5000. That's pretty close to our top-end GPU. That's available in a mobile form factor and a desktop form factor. So the key difference comes in at expansion capability. With the desktop form factor, you're able to expand, add more GPUs, add different peripherals, PCIe cards, et cetera, et cetera. With a mobile workstation, you're not. You're generally limited to what is physically inside the machine as it comes shipped. Now you can change RAM, you may be able to change hard drives depending on the model, but normally with the mobile workstations, the GPU that comes with it is the GPU that you keep for the life of the mobile workstation, and you can't add a GPU, it's soldered onto the motherboard.
Okay. And then a follow-on question for that, for the onboard workstation option, does the workstation need to be directly attached to the machine?
Yeah, so there's a couple of different scenarios, and I'm not an expert in machine controllers, so we would have to have that discussion, but it could be network attached. When it's network through an Ethernet cable, a LAN, when it's network attached, NVIDIA has solutions for high-speed networking, InfiniBand, et cetera, so that might help. But it may be possible, and this is what I don't know, that you could use a PCIe card from the workstation directly into the controller that would give you a faster throughput from the workstation to the controller. So you're either looking at Ethernet with InfiniBand or some type of PCIe direct connect. And I don't know which one would be better. I think that might depend.
Okay, and then it looks like we have one last question here to end on. It's a bit more of a future forward-thinking question. What role do you see machine learning playing in the AM software workflow? Is this a focus at NVIDIA?
Oh yeah, so machine learning is a focus on multiple fronts. Machine learning is a focus on well, on the geometry creation. So what kind of AI can you apply to, for example, generative geometry, generative design, computational design, using AI to autonomously generate heterogeneous materials that mimic mechanical functionality. So that's like a whole chapter onto itself. And I think, to me, that is just super exciting because it's going to change the way that we design. And I think that goes hand in hand with all the capabilities of 3D printers to design at the voxel level, to using traditional CAD software. You can't really do that. With generative and computational design, that takes the design process to the next level, but it's so complex, it requires AI to get involved. Now, the other side of AI is on the machine side. And you could use AI with, for example, intelligent video analytics for quality control inspection. So determine, are we getting a nice consistency on the output by using cameras that have been trained on what to expect and noticing if there's defects. We do this in regular subtractive production on factory floors, and I could see this being done, for first article inspection, et cetera, but throughout the entire production. The next level of AI is making, that I mentioned, onboard simulation. So reading in environmental factors, studying the output of the machine, and understanding, well, how do I need to adjust the printing parameters, the material composition, or whatever, to make sure that I'm getting better consistency. That can be done, that can be facilitated with AI. And at NVIDIA, we are investing very heavily in AI for multi-physics, so that you don't have to compute, because normally with CAE simulation, you have to take the model, take the geometry, and then run solvers on it, compute it. But with AI, it just happens instantly, because the AI knows, oh, based on what I know about this part, there's a problem here, and based on what I know about how to fix the problem, which is a lot, this is what we need to change in the parameters. So I see AI actually fitting onto the machine at some point to ensure quality control. And again, that's going to require GPUs on the machine for what we call inference, for picking up on those issues and applying them.
Great. Well, thanks, Sean. Do you have any closing words before we move to the next presenter?
Well, I think, we're just getting started here. So there's a lot of questions. I have questions. We all have questions. We're trying to figure this out. We're here to help. Anything that NVIDIA can do to help you, please contact us, just to have a discussion and brainstorm and figure out, where is this all going, and what are the right solutions in the short term for that yield the best ROI for you and for vendors, for your customers. Thank you.
Thanks, Sean. Up next, we have Dr. Brent Stucker with ANSYS.
Hi, everyone. Happy to be here. I think I finally got unmuted. Really, it's a pleasure to be here with this group. We have had over the years, well, in fact, I've been involved with additive manufacturing for almost 30 years now, and directly involved with a number of the people who presented over the last day or 2 days in a lot of initiatives over over decades. And for me, having been involved in additive for almost 30 years, it's exciting to see the acceleration going on in this environment today, particularly with respect to the kind of collaborations we're talking about between the types of parties that are involved in this DDC. And so what I'd like to do today is give you a little bit of background about who ANSYS is in this ecosystem, what we're doing in the additive manufacturing space, talk a little bit about what's new, what's in case you followed what ANSYS has been doing, talk a little bit about what's new, some updates, but what's next also. And when I think about, in general, the opportunities that are emerging, in my career, I was a professor for 18 years. And during those 18 years, a lot of what we had to do in additive manufacturing was prove out machines, prove out technologies, prove out materials, prove out parts one at a time. It was a very slow, iterative process to get parts ready for manufacturing and to get them approved to go into production if they're made using additive manufacturing. And one of the reasons I left academia and got involved in industry, and in particular in the simulation world, is because I saw an opportunity to change the whole dynamic. Instead of taking 4 or 5 years of a PhD project working with a company and a lot of researchers to get a part approved, we needed to have simulation, we needed to have machine learning, we need to have better, faster design tools. We had to, better machines, better materials. And by putting those all together with really good software, which is really what we're focusing on here in this Dyndrite partnership, with really good software, we can go to designing it, simulating it, building it, and getting it right the first time and going into production in a matter of days to weeks. And in some cases for heavily regulated industries, it might be months to a couple of years. But nevertheless, dramatically reducing the time by, say, 90%, even in some cases 99% of the time disappears for what it used to take to bring products to market. So I'm excited about that, and I'm happy that we can play a role in that future. Let me, first of all, just show you a little bit about ANSYS. If you're not familiar with ANSYS, we just celebrated our 50th anniversary as a company. We're one of the oldest software companies in the world. And let me just show you a little bit about what we do here with this video.
Before every innovation sees the light of day, and every robot learns on its own, before every automobile safely drives itself,
Keep right.
and every rocket ship reaches the stars, before every product is printed out of thin air, and every digital twin prevents a tragedy, before every baby takes her first breath, and every virtual reality becomes reality, before every student has the world at their fingertips, and every patient gets his sight back. Before all this can become real, there is a designer, an entrepreneur, an engineer, a student, a scientist, a visionary, tirelessly working to create a better world, using the most powerful, the most pervasive simulation technology on the planet. Before every product delivers on its promise, there is ANSYS.
This video makes some pretty bold claims. Really is looking at the impact of engineers and designers, entrepreneurs, visionaries on the world. And you look at the huge innovation that's occurred over the last few years, and absolutely, engineers, designers, innovators are behind all of that. And simulation has really accelerated that, and is starting to accelerate that in additive. So I'm going to show you the next little video clip about our additive portfolio.
Introducing ANSYS Additive Solutions, an easy-to-deploy, end-to-end software solution for additive manufacturing. From early design exploration to part validation, ANSYS offers a turnkey additive simulation process that covers it all. ANSYS Additive Solutions work with any CAD tool. Starring in the discovery environment, users modify their CAD, running topology optimization, making the parts lighter and suitable for printing. The parts then go through the build preparation process, cleaning up the geometry, finding the right orientation with our dynamic heat map feature, creating the supports required for a successful build. Next, the files go through the process simulation to ensure the parts will be printed first time right. This ensures success, giving you significantly improved ROI on your additive investment. ANSYS Additive Science takes the AM material analysis to a completely new dimension. You can perform porosity and melt pool predictions at the microscale. You can even analyze how microstructures will behave when the part is printed. This is critical to qualifying parts for production use, especially with the new materials and alloys used in the additive process. You can now capture and manage all your valuable materials data by adding on Granta MI for additive. Powerful analytics to establish the process property relationships. For part qualification, Granta MI ensures the traceability of your AM data. You can also access an unrivaled catalog of materials property data, fully integrated with your CAD and CAE systems. An end-to-end solution for additive manufacturing, only from ANSYS. Engineering what's ahead.
So obviously in a quick 15-minute presentation, I can't go into a lot of detail here, but I hope I've given you a little vision for the breadth of what ANSYS does and for the breadth within that larger community of what ANSYS does in additive. And so let me go into a little bit of the details on the additive side. Really, we're focused on 6 aspects of preparing parts for additive manufacturing. The first is the design side. How do you come up with the right geometry? And so, simulation has been used for many, many years by designers to help them finalize the geometry so that it gets the performance they want. And a lot of additive manufacturing is focused on how do we actually create new geometries that are maybe at the very limit of optimization. And so you need to do things like topology optimization and latticing and lightweighting. We have a bunch of tools focused on that. And in fact, those tools actually have some significant GPU-enabled functions that allow real-time, immediate feedback. I'll show a little video in a minute about part of that. But that's an exciting area. We've been working with NVIDIA for a number of years on some of those GPU-enabled tools there. Once you have a geometry, and again, each of these 6 items may be very iterative. In your design for AM, you might want to go through some build setup analysis, some process simulation, maybe some material analysis, then go back to the design and tweak it. And so this is iterative, even though we kind of show it in step by step. So build setup, that's just is my file ready to go to a machine? Where I'm going to place it in the build? What's the optimum orientation to trade off between, say, accuracy and speed and the amount of supports that you need. And so we have a lot of guidance to help the designer use that. Then we have these process simulation tools, which are really focused on as the part is being built layer by layer by layer, how is it distorting? Where might it distort and cause a build failure? And in order to overcome that distortion, we can do distortion compensation. If you can predict how to distort, then you reverse that distortion and compensate for it ahead of time. And I know that Harshil talked about some new APIs that they have to help with that distortion compensation. I think that's a very important area where you need a good intersection between the simulation results and the geometry engine to get a good distortion compensation. On the material analysis side, this is a really fast-growing area of our portfolio where we're predicting the microstructures and we're predicting porosity. And by doing so, we're enabling customers of open source machines like the SLM machines that were highlighted yesterday to much more quickly develop an optimum process parameter set for exactly what that customer needs. For instance, they may want to buy a powder from a specific supplier with particular chemistry. You can put that in, you can tweak the simulation to look at that specific material. And then you could say, maybe the machine came preloaded with a 30 micron layer thickness build set, but maybe I want to go to 40 microns and build faster, or maybe I want to go to 20 microns and have less stair stepping. And historically, coming up with that kind of material analysis took months of experiments, thousands of coupons, lots of cross-sectioning, and looking under a microscope and doing mechanical testing. And what we found with our customers using that material analysis tool is they can eliminate over 90% of the experiments and time needed to develop new process parameter sets. We also have this whole data acquisition and management side where you can capture everything about your AM operation, your log files, your simulations, your material assumptions, your mechanical testing, all of the things, and keep it in a nice database that then you can search through and even run artificial intelligence on to understand this massive amount of data that you've collected in your operations. And finally, on the part qualification side, that makes use of everything else, plus all of our traditional simulation tools to help you qualify your parts quickly. So if we think about all of this, you think, well, what's new? You know, yeah, ANSYS has been working in these 6 areas. What's new? Well, we come out with 2 releases a year in our ANSYS additive portfolio that fits in with the regular ANSYS update portfolio. And just to you know, what's gone on in the last release? Well, we've expanded our ability to do better optimization of the part orientation, where we can do stair-step analysis in addition to the amount of supports, in addition to looking at distortion and things like that. We've gotten more and more machines that we're reading to and writing from. We can now read and write from EOS and Renishaw machines. We've been able to read and write to SLM machines from the beginning, so they're already in there. We have others, but you know, really focusing on expanding that ecosystem. We're looking at in the additive print side, which is our process simulation side, you know, continuing to update our material models, getting more materials in there, improving our user performance, and then having ways of directly reading in data from even more machines. So in addition to the SLM and Renishaw and EOS, which we've done for a while, Additive Industries, we've added recently Trumpf and Sysma and HP3D. And again, these are focused on our laser powder bed tools. And then moving on even more in our additive science, which is where we're doing all our microstructure analysis, including more and more materials in there, and looking at, you know, the aspects of remelting of materials and how does that impact things. And then we have, you know, simulation tools, part of our normal workbench. If you're an ANSYS user, probably familiar with Workbench. We continue to upgrade that interface and give you more and more options to use higher fidelity meshes and more automatic detection of things that could go wrong, like recode or interference. And so if we think then about, you know, where are we going next as a company? You know, really, we're trying to build upon this strong portfolio and focus on bringing everything into a new defined environment. I'm going to show you a quick video on this environment, but within that environment, we want to be able to do all of these things, both design and optimization and build setup and simulation and post-processing of results and sending it directly to the machine, all from one user interface. We're also looking at better solving, better meshing, faster solve times, new machines, directed energy deposition, binder jet, and material extrusion simulations. I'll very briefly mention that right at the end. And just then expanding tremendously this ecosystem of partners that we work with, including those here in the DDC.
Hey, Brent, I apologize, but we're over time. So do you have a few words, final words?
Yep, I can just jump to the end and say, you know, I think, you know, really we're moving quickly to address the key needs of simulation and additive manufacturing. We really appreciate, you know, the partnership of the machine vendors, software providers here. And really, we think that interoperability, and this is one of the key reasons why we're a part of the DDC and working with HP, is because customers want interoperability between these different software tools, machines, and post-processing and all of these, so that, you know, they don't necessarily want a locked environment. They want to be able to work with all these different machines and materials and companies. And so we're happy to be a part of this.
Next up, we have Gareth Neal from XAAR.
Thank you, Brent. Now please welcome Customer Applications Manager, Advanced Applications, Technologies and Fluids, XAAR, Gareth Neal.
Welcome to our presentation on high viscosity inkjet and our TF technology. The recent developments we made in technology and some of the challenges that brings up with engineering and chemistry, and also design manufacturing, and a little bit about XAAR, how to work with XAAR in going forward. So we'll dive straight in about XAAR is once the slides advance. So we've been in inkjet printing, industrial inkjet printing for 30 years. We've been innovating in the space for 30 years. And we were instrumental in the digitization of wide format graphics and the ceramic tile industries in the 2D printing space. We turn over about £50 million plus a year. We have several, with over 300 patents with licensees of our technology, and we have several sites around the globe. We're headquartered in Cambridge in the UK. Our manufacturing facility is in Huntingdon in the UK, which is just north of Cambridge. We then have facilities in Sweden, Stockholm in Sweden, which is where part of the team I work for, AAT, are based. We have regional sales offices then in the US, in Dallas and in Hong Kong. Yes, so our technology, how we're pushing the boundaries. The XAAR print heads, again, next slide, please, if you have better control than me. So our print heads are true design intent with recirculation. They're very open architecture. Then this was initiated in 2007 with the XAAR 1001 print head. The fluid flows through the inlet, across the actuators, which are those trapezoidal features, and then out of the outlets in the manifold. And this forms the dominant flow of the inkjet print head. So this is far exceeds the ejection from the nozzles. And what that means is this can be a very high flow rate. So we can flow around up to 150 milliliters a minute directly behind the nozzles. This flow is constantly moving. This helps prevent sedimentation, allows us to carry lots of particles by weight in the fluid. It also is self-cleaning. Any large agglomerations get pushed around that recirculation and trapped in a filter rather than pushed into the nozzle more often than not. And it's self-priming. We're actively refilling the nozzles with pressurized ink rather than relying on capillary flow alone. This also reduces latency in the print head, so we're refreshing solvent in the nozzle to stop them skinning over and blocking, and it also regulates temperature. And what this helps to do in a development environment is it provides a stable platform for jetting. In 3D printing or advanced manufacturing, the product that you're making is what you're interested in. It's not looking after the print head. So having a stable platform allows you to develop better more often. And that translates directly into manufacturing uptime when you get to manufacturing. Now, we're not going to go too much into high viscosity jetting. We're just going to look at the established limits of inkjet at the moment, which are understood to be around 25 millipascal seconds. And we get there. What XAAR has managed to do with our technology is increase that limit with our standard print head to 65 millipascal seconds in our standard jetting mode. And in high laydown mode, which is an increased productivity mode in the same print head we'll come on to a little later, that viscosity limit is raised to 100 centipoise. And the slides will catch up with me eventually. There we go. So what does that mean in 3D printing? We get on to the next stage. So of the 7 types of 3D printing, 4 of them can be directly addressed by inkjet print heads. And within those 4, so we've got material jetting, binder jetting, powder diffusion, sheet lamination. You can do all of those with an inkjet print head. Within those 4 areas, the materials that can be addressed. So we can address metallics, ceramics, polymers, and within the polymers, we can do photopolymers, regular polymers, thermosets, thermoplastics. And with the laminated object manufacture, we can also address adhesives. The higher viscosity allows us to address chemistries which enable adhesives which are not open to inkjet usually. So the digital deposition can be added to those laminated object manufacture methodologies as well. And we can also, of course, do the normal color decoration you see with FFF printing or multi-jet fusion, for example. That color is also deposed by inkjet. So what I'd like to introduce you to is a customer of ours that we're working with Dyndrite called Additive. And what Meta are doing is a new type of binder jetting, which is not quite binder jetting, which is they're jetting a material which carries a high number of particles in its fluid, and these particles come in different sizes. So if we take the well-known analogy of rocks in a jar, and you're filling the spaces between the rocks with stones and the spaces between the stones with sand, and then the space between the sand with the liquid, what META are doing is applying something very similar to this binder jetting technology, where the rocks are the powder, the fluid contains micron scale particles, right, which is the stones. It also contains nanoscale particles, which is the sand. And then the liquid that carries these particles is also like the water within that jar analogy. The difference being that the liquid that META use is made from inorganic precursors, which also converts to metallics. So the part that you're left with, what you would ordinarily see as a green stage from a binder jetting process, so the middle picture that you can see on the screen now, is actually almost consolidated. It's very, very strong. You can tap these things on the desk, and they will not break. So the picture on the far right is after a thermal treatment of 10 minutes at 900 degrees C, and it's a finishing step rather than a main consolidation. And you can see from the polishing there, the density and non-porosity of that part. This should enable much larger parts and much more complex parts with reduced shrinkage and geometry, and taking that shrinkage from around the 20% region to the 2% region. Why this is important with and why we're working with Dyndrite on this is that nothing says that those micron, nano, or the inorganic precursors need to be the same metal. You can mix and match them, which means you can put them in different print heads. So you can have a metallic part which has different properties going through its body, and you need to slice that 3D model up and send the correct property to the correct print head. And you can see that once you start looking into blending the regions and getting into complex materials and complex properties, that the data required is going to get quite big quite quickly. So everything that the previous speakers have said about data rates and the amount of programming that's going to need to be done is entirely relevant. And these parts also are support free, so you can build metallic parts without supports within the powder bed, much like you would a binder jetting machine. So this is the main program we're working on with Dyndrite, but also for XAAR, the high viscosity capability of the print heads also translates into photopolymers. You can get more chemistry into the photopolymers, and that translates to material properties or increased material properties. You can have toughness, flexibility, elasticity with rebound, higher heat deflection temperatures, and higher optical refraction indexes, and a clearer definition between support and part material. So this hand you're seeing printed here is made with BASF materials that we've been working with them to develop. And there is no chemical or mechanical polishing applied to this. This is straight out of print head. All that's happened is the support material has been dissolved away in water. So the enabling, and there's combination as well. So you can also combine the particulate carrying with the photopolymers. And that's work that we have ongoing with some of our customers as well. So just some examples of beyond 3D for other applications. We also have applications in paint and coatings, biomedical, spin coat replacement, nano imprint lithography, photovoltaics, all kinds of applications where particulate carrying and or photopolymers or regular polymer chemistries enabled by higher viscosities are useful. So high laydown technology then. So from the same print head that you can address high fidelity parts, you can also address a high output printing mode. This is where we change the mode of the print head from operating at around 30 kilohertz for a 12 picoliter droplet to the same 30 kilohertz with a 400 picoliter droplet. So everything you're seeing on this image is printed with the same model of printhead. So the color image is CMYK, and then the texture on the bottle is printed at the same time in the same single pass with the same type of printhead. But that's a UV photopolymer, UV resin. So you can add textural effects, you can add texture to parts in a much higher throughput with a single pass. And there is a higher resolution, a higher magnification example of that here. And then moving on to other applications. Replicate embossed effects, so you don't need to spend money on expensive plates. You can do this with digital technology. You can then take all the optimization of digitizing a production line. And just to reiterate the particulate carrying, the throughput, and the high viscosity. Everything on this ceramic tile was printed by an inkjet printhead, XAAR inkjet printhead. So high viscosity capability is what's making the boundaries of inkjet, which is what we're pushing the boundaries of inkjet with. And high laydown technology is a massive step up in productivity for that capability. So not only can you scale with an inkjet printhead, if you want to print more materials, you add more printheads. If you want to print wider, you add more printheads. If you want to print longer, you just make the bed longer. It's inkjet is scalable for industry. We're also bringing more functionality into the region with our printheads. And how you work with us is coming up. But ImagineX is a window into our IP portfolio, if you like. So this is the areas that we're going to be focusing our technology on. So if you see something here that is useful to you from an inkjet printhead, then please get in contact and with us, with me, and we can take the project forward with you. And the way we do that is through our 5-step process. And again, I apologize for the delay here. So with our 5-step process, we believe on collaborations. The reason we're working with Dyndrite and MOTO Additive and other customers and partners is because we believe, in the same way that the other speakers have said, that collaboration is the way this industry is going to go forward. It has to. And we have a team of engineers dedicated to that within our department. And within the 5-step process, what you should have is evidence for stakeholders that your project is viable before capital expenditure. That's the point of it. And the 5th step of that is our unparalleled support network. So we continue to support you from through the development of your application into production. So our vision then is a world where you can print anything you can imagine. And I think that's the vision of everybody that's spoken today. So it's nice to be aligned. That ends my presentation. Happy to take any questions if we have time, Kristen.
Thanks, Gareth. We do. I think Harshil actually wanted to pop in and had a question for you.
Yeah, I was going to say thanks, Gareth, for dealing with technical difficulties in COVID era. But I think it's really cool. I wanted to dive in and highlight a couple things because I think what XAAR is doing is really fascinating across the board, right? Because one of the announcements that I made yesterday was around multi-bit grayscale printing, right? And the XAAR printheads come with how many inputs right now? It's like 4, right?
For grayscale level, we typically have 8, with one of those being not printing, so 7 printing grayscale levels.
Right, and so with that, of course, that's a kind of a unique technology, right? In that, if we can use those grayscales with those printheads, we can get to your vision, right? Printing.
Yeah, it enables another level of fidelity if you want it. You can print at the binary level and voxelize at the binary level, or you can voxelize at a higher level and tune your tune your properties using the grayscale and fill that voxel up with different materials from different print heads. So,
And what does that grayscale do for your print head? What is it controlling?
so it controls the volume of droplet from the print head. So the native drop size, so the regular drop size of our middle product, if you like, is 12 picoliters. What we can do is multiplex that 12 picoliters up 7 times to 84 picoliters. So if with that, you can, if you imagine the old dot matrix printer, and this is easiest way to describe it, you have very square edges to your letter O. If you were to put a smaller dot in between all those squares, and then smaller dots still between those smaller dots, to your eye, you blend out that pixelated effect into a curve. And that's what grayscale allows you to do. It allows you to create an apparent low resolution whilst having a lower resolution print head. So
what you're basically saying is with our API and your print head, you can do 3D anti-aliasing.
So yes, we'll say yes. Sometimes it's not quite that simple, but we'll say yes for
I'm trying to
without
boil
diving
it down
into
to super easy.
without diving into the technicals. Yeah.
Yeah. All right, those are the main things I wanted to kind of point out for the audience, because again, some of this stuff can be kind of lost because there's so many things going on. But at the end of the day, right, it's all about enhancing what you can already do. And as you mentioned, Gareth, right? I mean, XAAR has this history in the 2D world, right? And it's like, how do we take that and bring that to 3D? But of course, the data just increases in scale and size, right?
Yeah. So what we're aiming to do is enable our customers to address what they want to do is get something out of the machine at the end with a delivery method for the material. But in order to tell us what we need to position where, the same people need to be able to break their 3D vision on a computer down into data to send to the print heads. So how we're working with you is making sure that between us, we send the right data to the right print head to make the parts in simple terms.
So you're saying you need an engine that can properly transform and transmit data to a print head?
Yes, in 3D, the same as we have it in our 2D industry.
Got it. Sorry,
I think that's probably a good word to end, Harshil.
I'll let Kristen ask maybe more interesting questions, but
no, we actually that's all the time we have for this one. So Gareth, do you have any closing words?
No, I don't know.
Well, thanks for joining us. It was awesome to see all that you presented in a very short period of time. So nice work. Next up,
sorry, it was slightly rushed.
Yeah, these are short, quick little sessions. Thanks, Gareth.
No problem.
Next, we have Kevin Hahn from Aeon 3D.
Thank you, Gareth. Now please welcome CEO and co-founder Aeon 3D, Kevin Hahn.
All right, hello everyone. So before diving in here, I just want to take a minute to comment on how exciting it is to be surrounded by people who are so like-minded, focused on the same problems. And I think this really helps kind of create an environment for deeper engagement. So quick shout out to Dyndrite and the crew for their efforts in organizing. And the topic today is our outlook on not just preparing for or observing from afar, but actually helping drive finding the solutions to the challenges that we're going to face when taking applications of additive manufacturing from more science projects to what will eventually be a staple of the manufacturing and design environment. Coincidentally, this might end up tying together, I think, a lot of the topics that came up during the event. So Harshil, hope I'm not stealing any of your thunder. And spoiler alert, the thesis basically is that the best way to succeed in our minds is through very close collaboration among the partners in the industry, not just at the org level, but actually at the product level, because that's how we deliver a unified, consistent user experience that's built for them and not the people who are building the solutions. So for those of you being introduced to us for the first time, we build thermoplastic AM machines. And I think that today, this is still the image that pops up into the average person's mind when you mention additive. So as a hardware OEM, this is both a blessing and a curse. The curse is that we get blamed for everything that goes wrong, regardless of whose fault it is. Because for the average user, we're the point of contact for everything that goes wrong. If they have a question about a material or some part of the workflow. And there's, at the end of the day, it's a very natural thing to do. But so we asked ourselves, how do we see this as an opportunity instead? And we realized that we are actually in quite a unique position to be the one that, if we put in the effort, we can help, play a really key part in driving kind of the best user experience possible with this technology. So, everyone here gathered already knows that, it's not perfect yet. The user experience, the capabilities, the output, it's hard, but we know we can do better, right? So you might be familiar with this hype cycle curve from Gartner. Basically, kind of, it's a prediction on the sequence of, what specific technologies within the umbrella of AM, is going to be adopted. So the question is, where do we stand? And I think everyone in this room is going to have a different answer to this question. My answer, which might be a bit of a non-answer to some, is that this is actually a trick question. Because I think what we actually have here is a stark difference in the user experience between the haves and the have-nots. So much so that it looks and feels almost like two different technologies entirely. So on the have side, what do they have? They have the resources, they have the patience, they have the PhDs, they have the business, which allows them to make thoughtful investments into AM to gain a competitive advantage for themselves. And on the have-not side, we have what we might, call it more traditional manufacturing. And I don't mean that in a disparaging way. In fact, they have it harder because they're still building physical objects like we are, but without the benefits of kind of all this expertise that just like flocks to your job postings, without the business model like building airplanes, which allows you to make a lot of capital investments and investments into new process developments, improvements. And I think what we all want to avoid seeing at the end of the day is the wrong answer to this question. And again, spoiler alert, but this, if we don't do something to make sure that we're also thinking about, okay, how do we make AM work for everyone who can potentially benefit from it, not just the people who are already kind of building the technology themselves and working with it very directly on a day-to-day level. The only real solution is to start with kind of the user-centric mindset, and that serves as the kind of absolute foundation to everything. So yeah, of all the things we do, if I had to kind of sum up the overarching theme, this is it. And what this means for the user is, what if you didn't have to be your own systems integrator? Because if you had to go and kind of build an end-to-end workflow today, there's a lot of people you need to talk to. And you can do it. I think with everything that's out there today, there are more challenges, more technical problems we could actually handle than we might perhaps think. It's just that you need to search kind of the far corners of the world to make sure you're finding the right partners. Some at the NVIDIA scale, everyone's heard of them. But the person that holds the missing key to the puzzle to whatever problem you have might be some 5% consultancy somewhere in the world. So hardware, obviously. I think what's going right here is that there's a lot of variety, and this is good. Variety in terms of different technologies. We've had several just within the last couple of days here. Different form factors, like size, even something that trivial, can actually, obviously make a big difference between whether you can use it to solve a problem that you have or not, different price points, etc. And I think, what we've heard from our customers is that, at least in terms of the price point, this kind of mid-market, where it's not just like the MakerBots or the kind of the industrial, the original inventors, but in between there's a huge space for exploration and new targeted products, just in terms of the hardware design. But if that was all that was required, we probably wouldn't be sitting here today talking. So I think it's clear that this on its own is not enough. But based on the success that we've seen so far, what we've heard from customers, our philosophy, just, as a hardware developer, is okay. Whatever we build needs to be performant. Affordability or accessibility is actually quite important. And accessibility means, not just from like a money perspective, but as I was saying earlier, it touches on the expertise. If it's too hard to use, if you need to be an expert to use it, then that's a barrier to entry. And in terms of, what do we envision as like the role that, what we build serves in your professional life? It's a tool to serve you. So a tool doesn't kind of get up in your face and demand that, you spend every moment of your waking life thinking about, how do I make this work? It quietly does its job. Maybe you're interested in how it works, maybe you're not. But if you don't want to, if you just want to focus on what you do best in your business, then you should have that freedom, that opportunity. Second part, materials. So I am actually a materials engineer by training background, so a little bit of a bias, but we hear this from everyone else too, which is, we want more materials. Because if you compare the state of AM today to most other kind of established, mature manufacturing technologies, one very distinct difference is almost nowhere else do you have kind of the same limitations placed on what materials you're able to process. And why shouldn't we, as an industry, spoil them for choice? And the justifications for this are many. Obviously, from a technical design and engineering perspective, the more options you have, the more problems you could potentially actually solve from the different material properties that you are able to get access to. From an operations perspective, supply chain stability, you don't want to just, if you're going to use this for something critical, you want to make sure that you have a backup supplier for your raw goods, legal, IP protection, a lot of different reasons. And even if we didn't want to accommodate for this, I think the inevitable kind of forces of the industry are going to drive things in that direction. So we want to just embrace that and figure out, how do we give people what would make them most successful? And on this, this is almost more of a mindset than any kind of product decision that, just because you add a feature, that's not going to solve the whole problem either. We want to make a concerted effort to connect existing players and suppliers, all from the big guys like DuPont down to the more niche shops that are kind of creating their own custom formulations, connect them to the existing user base. And if you want to bring your own material, we can help you. Last piece, software, which I think we've spent a lot of time on over the last couple of days. And that's a great thing, because with great material choice comes a lot of complexity in terms of the analysis, the planning, the simulation. If you want to get it right, so if you want to have the flexibility and still get it the first time right, that's really hard. I don't think anyone has a complete solution to that yet. But we know that software is going to be a part of it, because that is by far the best way we know to deliver and apply knowledge and expertise at scale. And we also want to make sure that this, whatever we build can help empower all different types of users. not just PhDs, not just the people who know how to run and, perhaps, build their own simulation tools, but even for, someone who just wants to operate the printer, like they might operate a hand drill or something. We still want to make sure those are, the solution that we all build should serve those users as well. And yeah, and recognizing the important role that partnership has to play in building this, we need to make sure that existing workflows we can integrate. And this is kind of a mutual thing. Right, so, I think what I am personally looking for out of this is just to start conversations, right? Whether you're a user, maybe we've spoken already, but we haven't caught up in a while. I was part of the, Dyndrite Council here, or, you just want to wax philosophical about AM, I am totally fine with that too. So email's up there, and look forward to the Q&A. Yeah, thank you for all attending. And I look forward to the last panel as much as you guys, I'm sure.
Great. Well, thanks, Kevin. So if you have any questions that haven't been answered, go ahead and just shoot them over straight to Kevin. So up next, we have our closing roundtable on the future of digital manufacturing. We'll just dive right into it. First up, we have Dyndrite CEO Harshil Goel. Next up is Anthony Graves from HP and Sean Hilbert, the president of Cobra MOTO, which we saw earlier today. Blake Teipel, the CEO of Essentium. Gareth Neal from XAAR. And Dan Brunermer from X1. Great, so we have everyone up, it looks like. We have everyone? Here. All right. So because we have quite a few panelists today, we're looking at really, this is going to be a little bit more of a conversation and a discussion with really just one question. I think we've got a lot of passionate, strong personalities here, so I don't think we'll have any trouble filling up the 30 minutes. With that said, I love it on panels when people challenge each other and question each other, so, have at it. So the question that we're addressing today is really pretty simple. Just what are your thoughts looking forward into the digital transformation of additive manufacturing? What needs to happen and why? Harshil, do you want to kick us off here?
I'll summarize by maybe talking about, I think, the two key themes that I've heard over the last couple of days. One, of course, is software, which, is a little self-biased. But the other one, which I think kind of has been pervading throughout this, is I'd call democratizing additive, right? This concept of not necessarily needing, multiple PhDs or multiple specialists and experts to go and run and operate these machines, right? And there being kind of a distinction between folks who are doing hardcore R&D to push the bleeding edge, like on the print heads, for example, versus, going into production and needing software and solutions and machines that are just enabled, right? So I'm curious if anyone else on the panel saw a different theme, or was I just kind of, did I capture both key themes?
Yeah, I guess I'll just jump in. So, certainly the software tools, have got to improve, and they've got to get easier to use. The user experience matters just as much as what the software does or doesn't do. But, at the end of the day, it's also cost, I would say, right? I mean, cost, but not just a cheap or a low cost solution. It's really a figure of merit problem where you sort of say, what's my cost per unit output, right? Because additive has got to chop, it's got some wood to chop here as an industry to really show and educate folks around how these costs have, in many cases, already come down, and how the costs are actually already sort of, ready to go, and they're accessible. And in fact, engineers can typically get this, but we see finance professionals, we see accountants, we see sort of procurement and purchasing groups at large companies struggle. They fumble all over themselves trying to understand, how do I build a cost model when I'm, looking at piece per piece cost from an injection molding or a legacy technology versus additive. Maybe the piece costs more. Yeah, but look at all those adjacencies, right? Like the mold design, the mold storage, the amortization, keeping up with rev changes years out into the future, again, with your mold. So there's more we've got to talk about as an industry. I think all the panelists that would join me today could agree. If we can talk more about the true cost picture and how additive is already highly cost effective and much more so than many people think. I think that's the next frontier, as well as certain software and some technical things. But the procurement. Can you afford to procure an additive solution? Yes, and here's how.
I'd like to riff on that a little bit. Yeah, costs are a big deal, and we went through that. I don't know who heard and who didn't hear the conversation earlier that Anthony and I had, but one of the big things we had during the economic downturn was insourcing and home sourcing a lot of things that were overseas. And one of the big questions we had during those days was, what is the cost comparison, right? And at that time, the kind of the moniker that everybody used was, well, what's the China price? And the reality was, when we started really digging into what the true landed cost of a part was compared to what we could make it for, the difference was way smaller than what we ever thought it was. And the reason was because nobody was taking proper consideration to what we were calling soft costs. And soft costs are the cost of communication, the cost of, in some cases, it's the cost of transportation when you have transportation delays, when you're stuck in customs, when you have to have people day after day chasing after items that are on their way in the door. And you never properly take into account those kind of costs. The cost of quality, what happens if you have a container load of stuff show up that you can't even rework? I mean, how do you put a true number on those kind of costs? And the answer is nobody does. Nobody puts a high enough number. Nobody puts a high enough number on the cost of capital when you have large minimum order quantities. And so I agree that cost is really important, but I also think that the way we analyze costs is not nearly sophisticated enough. It's out of date, and we have to start really putting some hard numbers on soft costs, because when you do that properly, additive looks more and more and more attractive all the time.
Yeah, if there's one message I'd love for us to take forward to the world in 2021 as a community, it's like, sure, let's talk about the latest and greatest feature or material or whatever, but let's all together talk about costs. Let's talk about how cost effective we are. Let's all develop narratives that we can take together to tell the world, hey, additive is cost effective. We're ready because of the agility that we provide, because of the flexibility we provide, and the insurance. We're like a time machine and an insurance policy baked in. So those things need to get talked about a whole lot more, I think. And the good news is it's not a difficult message. It's just kind of an unusual message for people who are classically trained as technologists, right? So we need to think more like the accountants and think more like the procurement folks. That's how we unlock it, I think.
Hey, Harshil, if you want, I just one quick comment, and it's this one thing that I don't hear spoken about enough. I think there should be an event just on TCO and production costing around additive manufacturing, like literally a conference where we have a bunch of people come in from these different companies with different experiences. Because I'll give you one example. First of all, in most of the conversations that I have heard over the last decade, post-processing costs are very rarely rarely mentioned or rarely accurate. That is super important. It's important on both ends. If you're comparing it against traditional manufacturing processes like machining or fabrication or injection molding. And then the second thing is warehousing. One of the problems, and I mentioned this earlier, was that it's great to be the person that's like the newest to market, because hopefully you've learned from everyone else's mistakes, and you've been able to come out with a better, faster, less expensive product, solution, process, whatever. But the reality is that the big companies, and the big companies, the people that have been around a while, have the constraint of having a lot of customers, a lot of market share, and they can't be as agile. And one of the things that's hit the big companies, whether it's automotive or it's appliances or consumer products, is that the big companies operate at a completely different accounting mindset, where young companies that are agile and they're making 5,000 parts and that are iterating, and another 5,000 parts and iterating because of additive manufacturing, they have multiple benefits. First, they can be more agile, and secondly, they're not producing 50,000 parts to hit at some arbitrary cost, which isn't accurate to begin with. And then they take those 50,000, they ship out 20,000, they put 30,000 on the shelf, and they end up, selling to, some wholesaler 25,000 of the ones that are on the shelf, so they don't have to keep them on the shelf. And it's just the amount of waste. So this whole issue about, I think people look at the cost to print a part, and that's not the whole cost. But at the same time, it's not just the cost to print a part and post-process the part. It's the fact you don't have the cost of warehousing, and you can be more agile and more competitive. So I think it's an awesome topic. It deserves a whole nother 2-day event.
Well, it does, Anthony. It absolutely does. And I think we should schedule it in like August, because you start to see like fiscal years that are ending in September, right?
Yeah.
End of August. So we should schedule this event now. I'm talking to the community here, guys. Let's do this.
I thought you were talking to me.
Let's do this, Harshil. Yeah. Yeah. And so then it's like, then you've got the end of people's fiscal year. You've got a cost-focused message. People may have fallout funds or whatever other unused discretionary spending they can allocate to some technology. And they may be asking themselves, is this technology ready for prime time? Can I trust the technology? Is it cost effective enough? Well, yes, it is. And here's how. And so we not only do we have the event, we time it.
Yeah, just one last quick comment following up on that, Blake, and it's this. Companies have to pick apart. I always say, before I joined HP, I would tell companies, pick apart. You've got 3 million in your catalog, you've got 560,000 in your catalog. Pick a part, buy a printer, and buy the equipment to run, and see what the costs are, because it's that first step that I've seen to be the most prohibitive thing that larger companies are facing. They won't just pick apart. They'll prototype all day long, but for production, pick apart, run it through the process, put it into production, put it in your product that's out in the field, and see what the real costs are. And I think they'll be surprised when they do that analysis and they include things like warehousing, how many benefits there are to additive, regardless of the materials, regardless of the process.
So I think that's a fine point, but I'll say in terms of like software that's missing, that's kind of a big one, isn't it? Because who the hell wants to go through a database of 600,000 parts to pick apart? Like what people are asking for is funneling. Like they want to have a product that they can say, okay, I want you to go search these 10 directories of my 600,000 parts. And I want this intelligent software to identify the top 100 candidates for me. And then I'll go through and do the finished picking or whatever. But to me, that's a big, huge hole. We get asked about that all the time. What kind of software is out there to help me identify those parts that are ideally suited for additive, in our case, binder jetting? But I wanted to take a different little swing at your original question there, Kristen, about what I think moving forward and what has to happen and why. So as technical fellow, luckily, I don't have to get too bogged down in all these cost discussions. And so the way that I'm focused on expanding additive acceptance throughout industry is that I focus on two things in my role here. I'm the head developer of our educational programs that we promulgate through universities and through community colleges. I go and teach classes and blah, blah, blah. I mean, I think education has to be pushed down. I think in some ways, I feel like my kids know how to use a table saw and an oven because they were taught home ec and wood shop in 7th grade. And I feel like we need to keep pushing technology down. I mean, there was a time when calculus was a college course, right? Now it's like 11th grade math. So, I think we need to continue those kinds of things in terms of our education system. And the second thing that I do is standards. I work for ISO ASM. I'm head of the JG 57 committee, writing 52911-4 standard guidelines for binder jetting. I was part of the SAE committee that wrote AMS 7022. An aerospace spec on binder jetting. And I think that the standard space is absolutely vital for acceptance of additive, because if Cobra MOTO was, say, a tier 1 supplier to a big 3 automaker, you're not going to buy a single additive machine if you don't know for certain that you can put in a set of parameters and a set of materials, and you're going to get parts out with a very specific set of material properties.
Yep.
So those are the two things that I'm focused on that I think absolutely have to happen for additive acceptance.
Yeah, that's an awesome point.
I think I
Awesome.
agree with all of you. There is an analogy that I can bring. So in my presentation, I had a picture of a ceramic tile that had been inkjet printed. They all used to be screen printed. So for each individual color, you had a screen. You had to store all those screens for each design. You had different screens. You had to clean them, all that solvent waste, all the particle waste. You build your tiles to batch. And then you have to hope you sell that whole batch. And then if somebody comes in with more, you have to try and match the colors. Everybody remembers going to the hardware store with the wallpaper and the tiles, trying to get one that matched what you already had. Right. And that is now done digitally. It saves waste, it saves inventory, it saves warehouse space. It's analogous to some of the lessons learned in 2D printing. So yeah. It has been done, and it can be. There is experience to draw on, and we can do it again. And Dan is absolutely right. For this industry to industrialize, we need to provide the metrics that industrial suppliers of components want to see. You need to be able to dial in your parameters, get the material properties you want, and supply a quality chain to prove that. Those are the questions that need to be answered.
Yeah, I think that's right. I think education and standardizations, those are huge things. And a lot of people still try to compare additive to subtractive on the material properties or on the education. Is this a drop-in technology? Could my specialist who's trained on using a CNC mill or a G-code enabled machine, can this person use, an additive machine? I mean, an extrusion, sure, but in any technology, there's going to be an educational curve that you've got to come across. And those are really vital mid to long-term items that take a long time. They have a long tail. They take a long time to scale and get out there. I think they're vitally important. I couldn't agree with you guys more. I do think that the neat thing about talking about cost more is that it's kind of something that's already there. It's just sort of us repackaging a lot of that data and repackaging a lot of that conversation. And we can sort of change the narrative starting now, because there are so many examples of people like the story shared earlier at Cobra MOTO. You guys dove in. You guys adopted an additive technology. You chose 1 or 2 or 3 parts to comprise an engine, and you guys decided to dive in. Now you're a small to mid-cap business, so your risk profile and your bureaucracy are all sort of lending themselves to you guys making a decision like that and diving into a new technology. And not all businesses are built like that. Again, strength to the small and mid-cap business. But taking that courageous step and diving in, building the use cases, building the inherent on-site education, and demonstrating the win, that's all massively important parts of the journey. And they can start happening now, I think, which is exciting.
Yeah, I agree. And one of the things I promised our AM technicians is, hey, we're going to put together an apprenticeship program for you guys, just like a machinist apprenticeship. But we don't even know what that looks like, and we don't know. I mean, maybe there's folks out there that are developing, and I'd love to know if anybody is.
Hey, I can definitely help you with that.
Okay, wonderful.
Yeah, I mean, there are educational initiatives here in Central Texas. Austin Community College and the Texas Workforce Commission. Because of COVID, we basically got connected with. We were producing face masks. We produced like 60,000 in 90 days, and so again, our costs were competing with the China cost. We were beating the China cost. We were providing face mask frames in that moment because of supply chain disruptions and all these other things. And we used extrusion additive, and we printed nylon frames, and then we put those in a kit with like a Swiffer sheet, that was basically electrostatically charged ASTM level 2 safe for community use sheet. So we put together a solution. We beat the costs that were available at the time. We used additive in situ, the materials, machines, and the software at the time coming together. And, the kits were over 3.9 million face mask usages, face mask equivalents. We put that whole thing together in 90 days. We ran it, the whole thing. And so, and we did a material changeover in the mix, right? We went from a TPU to a nylon. And so that kind of thing's just not possible and subtractive. We've all had stories like that where we've got examples of use cases. So that caught the attention of the Texas Workforce Commission and Austin Community College. They're putting together now advanced manufacturing training courses here in Central Texas. So at least we're starting to get some traction educationally because we were able to talk about the cost model though. Until I could frame it out and I could say, here's the per piece cost. And by the way, here's the CapEx and the OpEx that it took to put a fleet of 12 of these systems to work for 90 days. And here was the output. Then they were like, oh my gosh, there's no way we could have done that without using additive. Again, it's the insurance policy, it's the time machine. And it was all based on the cost model because everybody had seen some like example of a 3D printed part and like, oh, that's cool. I went to my public library and I used a MakerBot and that's cool. But like, folks who run community colleges or who make policy decisions or educational decisions, they're not the technologists. They're the cost people at the end of the day. And that's why it was important to have that story.
Pull it back a little bit more towards the digital transformation side of things, and blend a couple questions that have come in from the audience. So we've seen it from a lot of different people with different technologies throughout these last 2 days. Binder jet, FDM, and we've been talking a lot about what needs to be done here going forward. How are we going to set those priorities, and who's gonna take this initiative? Because I think we have a lot of these conversations, but how is it going to really truly be driven forward and put into effect?
I mean, a common theme of this whole session has been collaboration, right? Mm-hmm. But I think if we try to focus on collaboration from the lens of capability, while that's important, that's going to be challenging to get all the different like parts of the code stacks aligned. And again, that can be done. But I think if we can adopt, standardizing, the comment Dan made earlier about standardization, right? If we can adopt standard like communications protocols, if we can say machines, that are talking to themselves, like an Ascentium HSE to an Ascentium HSE, but then an Ascentium HSE to an MJF, which is talking to a CNC mill, that's an area where I think the community should focus, is standardizing on the communications protocols and solving from the lens of security and encryption, making sure that the warm blanket is provided to those organizations who are using, who are allowing machines on their network or machines to create their own network. And so I think that's something that we could really make a big difference on in the near term. It's not, okay, yes, we have to align code stacks and have the APIs and all of that. And I know actually very little about that. So that's where you guys come in. But like the security and the capability piece, I think that's a big piece that also we could solve together.
One thing to follow up on what Kevin, who was presenting just earlier from Aeon 3D, mentioned, there were two things. I think it was on his last slide. I can't remember. One was there isn't a one-size-fits-all solution. And the reason I mention that is there are and there ought to be one-size-fits-all standards as much as possible, like communication protocols. Blake, you spoke about that yesterday in your presentation. And there are other aspects just like that. And while we're all trying to complement each other's workflows, because ultimately that's why we need to have these standards. There are going to be companies that have 25 Aeon 3D printers, and they're going to have 25 Ascentium printers. I don't want to leave anybody out. HP probably have 25 too. But they all have to work together.
Three because the HPs are so productive. They only need 3.
Yeah, that's true. But it's not just the software, it's the hardware. Everybody has to come together. And I think we're in all violent agreement across the board. And a lot of companies, I won't name any in particular, but there are two that were relatively restrictive over the years. Just in the last year or so have really opened up to the market and to working with other OEMs. And that is a huge sign. That's a good sign. And we're headed in the positive right direction. So, the question is there like one process? There's never going to be one process. It's not going to happen. Well, not in our lifetimes, I don't think. But I think we should keep the one size fits all or those types of discussions to elements of the overall picture, but not the overall picture itself. So, and Dan might have a thought or two about that as it relates to the standards.
Yeah, well, I'm sorry, I missed part of that. My network choked like right in the middle of something there. But you know, I'll say that that's a huge topic also, right? So another panel I sit on is with NIST, and NIST is working on something that they call the Common Data Dictionary, and there's a whole bunch of people there. I mean, not just me, and it's mostly right now focused on laser additive metal, but that's what they're trying to do, right? Is come up with like a pedagogy that industry can agree to. And, you know, I mean, those discussions are fun and whatnot, but you know, when you start talking about arguments like, well, I think the variable should be named laser power. Well, wait, shouldn't it be like power dash laser? And then you go into a 5-minute discussion of which should be the
Dan,
right
you're
tab
getting
name.
into fighting. You're getting into fighting words.
Yeah, well,
melting,
right. You know what I mean?
Right. Or direct,
you know, so like
director
you
from the
wind up in
side.
those discussions, and that's why I'll say, you know, the last thing that I would say is, and this is where I'll go ahead and be the curmudgeon and say that that what additive really has to do is get over itself. Like additive thinks that it's the first industry ever to face unitized production optimization problems, as if that hasn't been going on for 200 freaking years, you know, right? And so like when I think about computerized naming and ICAM, you know, like we're talking about concepts that go back to the 70s, not concepts that were invented last year.
Right.
And Dan, it's kind of amazing how we call it build prep, not additive cam. You know?
Right.
Exactly. Why isn't it called CAM?
It should just be CAM.
When they named it additive manufacturing, I was like the only person in the room arguing for additive machining, because I kept saying it's just a machine that adds things. Why are you letting CNC own the word machining? And oh, that's too challenging. As if additive.
Dan, you were right. We should fight that battle again. We should fight. The one thing that we say, and I think we all need to get, maybe this is another thing that we can all parrot, and manufacturing itself needs a change in mindsets and tool sets. Tool sets out of necessity, mindsets from a business perspective also out of necessity. People need to think differently. It's not a cliche. The people that are thinking differently, and broadening their expectations and vision of what manufacturing is, they're the ones that are going to be successful. Everyone else is just going to be chasing along behind them. So, but we have a great core group of people in the DDC. I mean, it's up to us at the end of the day. It is, like you said, Dan, it's up to all of Blake. It's all up to us. If additive doesn't take off, it's our fault. It's no one else's fault.
Anthony, are you going to change the name then from Universal?
It's really
Build
Dan's
Manager?
fault.
Yeah.
What's that?
Are you going to change the name from Universal Build Manager?
Maybe it'll be HP Cam, but then we're gonna have all the cam companies raising hell. You know, I'm not gonna even list any of them. So we'll keep it UVM for now.
But listen, let me ask you that question. At what point does the additive industry get so big that a company like Sprute Cam says, you know what, I'm going to make a G-code generator for additive? Sure. They do it now for 5-axis CNC. How much harder would it really be for a locked-on cam company that's all they do to make an awesome cam generator straight out of a CAD program? I mean, you know. No,
absolutely. And even internally, we call it, we've referred to it internally on my team as CAM, and that was my background. A lot of the people on my team came from HSM Works and integrated CAM for SolidWorks, and then working also with all the other ones, the master cams, edge cams, Gibbs cams, et cetera, et cetera. You're 100% right. And the reality is that maybe some of the smaller ones might take a look at additive. The big guys have their hands full, but you're right. There's nothing, it is just a decision that somebody has to make. And yeah, there's nothing stopping anyone from getting into the business.
So we only have about 5 minutes left, and there's a few questions that have come in. I think we're gonna do this one to make sure we get one more in. Question is, coming back to printer parameters and materials, ANSYS was talking about simulation and optimization of printer parameters for various materials. But for this to happen, the materials have to be characterized very well. That takes time and effort. In your opinion, how important are solutions that speed up R&D, printer parameter, and materials development?
Was this question like directly to Ascentium, or should I just?
I was gonna say, I feel personally encouraged. But
Yeah, no, I promise you, we did not see that question. Yeah, I mean, look, the whole concept behind like high-speed extrusion, just for 2 seconds, is basically to speed up characterization and certification of materials. Like, we basically realized that if you can print parts much more quickly, then you can print S basis or B basis, statistical samples that you need in order to gain airworthiness certs, in order to get an airworthiness circular put out by the Air Force Research Labs and Lifecycle Management Center and NIAR and CART and all these folks who've done this. You've got to print a lot of parts. You've got to do so much more quickly. And so regardless of the technology, whether it's extrusion or whatever it is, you've got to speed up the dang robot and get the parts produced more quickly, or it's another $4 million to do a certification of another material. So machine speed is just as vital as software speed and so forth. It's all got to get faster.
I was going to add, from my perspective, it's on the software side. It's why we are making all of these open toolpathing APIs, right? In order to try these different materials, they're going to require different toolpaths, whether it's a HSC process, like a XAAR printhead process, an X1, process, or even a laser powder bed, like SLM type process, right? They're all going to need to be controlled by different toolpaths. And quite honestly, the number of times I've seen people manually put boxes on a plate at different orientations and angles with different toolpaths is kind of insane, right? Like, they should be able to do these DOEs, not in a prototyping sense, but you should be able to do DOE with a production mindset, right? And to me, that's kind of the idea of saying we're going to qualify and classify materials with a production mindset, right? And that requires open machines, open software, and just a different philosophy, which I don't think Additive has had, quite honestly, until very recently.
That's great. Well, we only have a few minutes left, so anyone have any parting words?
Well, I certainly would like to say we're excited to join the Developer Council. We're brand new to the community. This is our first foray, and we're just excited. HP and what you guys are doing, and Dyndrite and others. I think this is very important. The future's got to be based on platforms that are open. They're open platforms. They facilitate the best solutions to be used by the client. And so I'm excited to be, we're excited to be part of the community, and we're excited to, just join in and do what we can to help make additive manufacturing more like actual manufacturing.
I think I'd just like to echo that sentiment, and XAAR is built around all our customers, but especially the advanced application customers around an education base, and we're an open platform printhead supplier. We give you the opportunity to put your material in and learn and walk the journey with you on whether it works or not. And the collaboration is how I certainly see XAAR and 3D printing moving forward, because the component suppliers, material suppliers, the software, the machines, you can't do it all unless you've got massive pockets. So collaboration is the only way, and we're set up to do it that way.
Gareth, I'd actually argue that you can't do it all, even if you have massive pockets.
There's still time is still a factor, right?
I was going to say, we have multiple multi-billion-dollar public companies failing at the moment to do everything all at once, right?
Failing is learning. Let's be positive.
Right.
Failing is learning unless you're holding back an industry because of your arrogance. Then failing.
Right.
Failing is just.
Then failing's failing.
A jerk.
The first step is recognition.
Right.
It's coming. I think the discussion is the first step. I think we've moved beyond discussion. We're starting to see people do something about it. So it's coming. It's exciting.
Well, I mean, Anthony said it in the video, right? Choose wisely, right? If you don't pick an open platform or open partners, right? Or, what Blake said earlier about how the US Air Force, like CTO, literally said they won't buy machines unless they're open, right?
And a report to Congress. It wasn't like an internal memo. It was like a report to Congress.
Yeah, that was yesterday. That was like one of the big takeaways. And what Dan said about the automotive industry, if you don't have characterized materials and processes, and like you said yesterday, if the government if they start to standardize and they start to mandate things, you're either going to go along and or you're not going to be participating in the big picture. So I don't think we'll have a problem with any of that, but it is important, and those kinds of statements it's a constant reminder to the industry that, look, we have a lot of work to do, right? So it is very interesting. And I just want to say, I want to thank Sean, who's sitting next to me here at Cobra MOTO and Cobra Aero, for participating in this with us. I'm glad we got to hear his perspective as an end user, because eventually he's going to be buying stuff from everyone here in the room. And I appreciate the event. I think it's a unique event, and I look forward to the next one. And welcome XAAR and Ascentium to the club, to the gang. It's more like a gang. I think we need to make Dan the ringleader. I mean, I know Harshil's the gang leader, but we need to make Dan the ringleader. But it's fun, and we're happy to participate and help sponsor the event. So thank you, Harshil.
I wanted to say thank you for that endorsement. I'll just give a quick plug. If there's anybody in the audience who would like to learn more about how to participate in standards like SAE, STM, ISO, or any of the other bodies, please feel free to reach out to me. I know that Harshil has my contact information, and I can help you get put in contact with your particular mode and what kind of committee you might want to serve on.
Well, Dan,
Great.
we'll be in
Well,
touch.
I think we're going to head now
Thanks,
into
Well, I know DDC 21 is coming to a close. Thank you all to the folks who stuck around. As you saw, a number of the things are going to be posted online, and they're already being posted online. Hopefully, we can also make some clips in case you don't want to watch the full 4-hour Odyssey. But I do want to again take just a brief moment to just kind of recap what happened today. We had Anthony Graves on to talk live from Cobra MOTO about what they're doing, how the Universal Build Manager powered by us plays into things, and how it is a truly universal solution. We had an awesome talk by Sean Young showing the value and the importance of compute in the manufacturing space. I believe that we've used GPUs far too long for just putting pretty pictures on the screen. It's now time to use them more for computational geometry. And of course, an NVIDIA A5000 is probably the best version to use our software with. We then had a number of presentations from Dr. Brent Stucker from ANSYS, Gareth Neal, a new DDC member from XAAR, and Kevin Hahn. We had, I think, a pretty lively closing roundtable. And if you could take a moment to just take a brief poll, just so that we can honestly help improve these events. Let us know what we did well, what we didn't do well. Let us know which presentations you liked, because we are continually trying to improve, how we throw these things. So with that, again, thank you for attending DDC 21. Hope to see you at AMUG, and hope to see you hopefully in person as folks, start to travel and get vaccines. And yeah, thank you for your time for the last 2 days. Appreciate it.
We still seem to be dealing with some of the same software limitations we had going back to the beginning. We need to be able to think about things on a mass production basis. Additive needs to graduate to the level of efficiency that we see in some of these other more traditional technologies.
The future of additive is production. HP has decades of experience automating the commercial printing industry, from business cards to books. Our tools at their core need to be able to support massive amounts of data and process this data very quickly. This is why HP's collaboration with Dyndrite is so important.
Dyndrite's mission is to fundamentally change how geometry is created, transformed, and transmitted on a computer. Just as PostScript and the Motorola 68K enabled the desktop publishing revolution, Dyndrite and GPUs will define digital manufacturing. Imagine the wonderful things that people will create, the lives that will be improved, and where humanity will go as a result of this. That is the promise of additive manufacturing.
The companies that will dominate manufacturing for the next 30 years will be choosing their technology over the next 24 months. Choose wisely.